Hi everyone, and in this amazing course we're going to uncover the React function components and hooks that really change the way we're building modern applications. We're going to start from the very basics, so I'm going to talk in this course about JavaScript, then we're going to move to jQuery as basics to explore the React component-based approach. From there we're going to focus on function components like props and reusability, and then dive deep into hooks such as Usestate, Useeffect, and then custom hooks that let you manage state and side effects cleanly. You'll learn how to design scalable applications with components and build apps that feel dynamic. By the end of the course, you'll feel comfortable building production-ready React applications that will definitely help you to boost your career as a developer. This is why I would advise you to watch this course until the end and also pause the video along the way and try tweaking things yourself. Also, if you have some questions or comments about the course, please write them down in the comments because usually I respond to all the comments under my videos. Make sure to like this video and subscribe my channel for more free tutorials like this one, and you can also access the full code for this video linked in the description. Now let's jump straight to the course, and I hope.
In the world of React development, managing state within functional components is a crucial skill that every developer should master. This aspect of React allows us to create interactive and dynamic applications that respond to user inputs effectively. Today, we're diving deep into crafting states in functional components, a fundamental concept that empowers you to manage data changes over time within your application. Now let's take a look at how to implement a simple counter using the *Usestate** hook. We begin by importing the necessary React module and the Usestate** hook. Then we define a functional component called *counter**. Within this component, we initialize the *count state variable using *usestate**, starting at 0. This allows us to keep track of the current count. Next, we create the *increment count** function, which updates the *count* state whenever the user clicks the increment button. By calling *set count* with the expression *count plus 1 *, we ensure that the count value increases by 1 with each click. This showcases how state can be modified dynamically in response to user interactions. In the return statement, we render a *div* that displays the current count in an *h1 tag and a button that triggers the increment function. When the button is clicked, React automatically re-renders the component to reflect the updated count. This simple example effectively illustrates the core principles of state management in functional components, demonstrating how states can create dynamic and interactive user experiences in React applications. Now let's see how we can implement an authentication feature using state management in our React application. In this code, we start by importing React along with the *Usestate** hook, which allows us to create state variables within our functional component. We define the component authToggle, where we initialize a state variable called isLoggedIn, setting it to false, indicating that the user is logged out initially. Next, we create a function named toggleLogin. This function reverses the current state of isLoggedIn whenever it is called, effectively toggling between logged in and logged out states. This direct manipulation of state illustrates how we can control user interactions through events. The rendered output contains an h1 element that displays a welcome message or a prompt to log in based on the value of isLoggedIn. Additionally, we have a button that changes its label between log in and log out, corresponding to the login state. When the button is clicked, it triggers the toggleLogin function, allowing real-time updates to the UI. This demonstrates a practical application of state management, enhancing the user experience by providing immediate feedback to user actions. Next, we will implement a user form that captures both the user's name and email address while managing the state efficiently. In this component, we utilize the Usestate hook to create a single state object called useinfo, which contains both name and email fields initialized to empty strings. Now let's look at how we handle input changes in the form. The handleChange function is designed to listen for changes in the form fields. Using event destructuring, we extract the name and value from the event target, allowing us to dynamically update the corresponding field in our useinfo state. This is accomplished by using the spread operator, which ensures we maintain the existing state while updating only the relevant property. When users submit the form, the handleSubmit function prevents the default form submission behavior and logs the userinfo object to the console, allowing us to verify the collected data. This implementation simplifies managing multiple pieces of related state, demonstrating a clean and effective way to handle forms in a functional React component. Next, we will implement a more advanced version of our user information form that incorporates conditional rendering based on user input. The primary feature added here is the ability to display a confirmation message when the user enters their email. We start by defining a functional component called *** enhanced user info form, utilizing the ***state** hook to maintain a local state object that contains the user's name and email. As the user types into the form fields, the *handle change ** function captures these inputs, updating the state accordingly. This approach keeps our form reactive, as changes in the input fields immediately reflect in the state. After the user submits the form, the handle submit ** function prevents the default form submission action and logs the collected user information. Now let's look at the conditional rendering aspect. Inside the JSX, we check if the email field is not empty. If it holds a value, the component renders a message acknowledging the provided email and thanking the user. This conditional rendering enhances the user experience by providing instant feedback and keeping the interface clean and focused without overwhelming details. Such integration of state management and rendering logic exemplifies how React can create responsive applications. Now let's implement the following reset functionality in our enhanced Useinfo form. This code begins by importing React and the Usestate hook, which is essential for managing component state. Within the functional component, we initialize the Useinfo state to hold the name and email fields, both starting as empty strings. Next, we define the handle change function to dynamically update the state whenever the user types into the input fields. It captures the name of the input and its value, ensuring that our state reflects the user's input accurately. The handle submit function is where we handle the form submission. It prevents the default form behavior, logs the user info to the console for feedback, and crucially resets the form fields by invoking setUserInfo with the initial state. This resetting is important as it clears the inputs after submission, allowing users to enter new information easily. Finally, we return the form structure, including two input fields, one for the name and the other for the email, while ensuring they are controlled inputs by connecting their values to the userinfo state. This design not only manages the state, but enhances the user experience by simplifying data entry. Before we conclude our journey through state management in functional components, let's briefly touch on the common pitfalls developers face. It's easy to get tangled in state updates, especially when dealing with asynchronous code or multiple pieces of state. Using the functional form of the state updata, like we've demonstrated, can often prevent stale state issues. Always remember that React batches state updates for performance optimization, so your state might not immediately reflect changes after calling the updata function. Another important aspect is reasoning about your component state. Aim to keep your state minimal and avoid unnecessary complexity. Structure your state to be as flat as possible, as deeply nested states can become cumbersome to manage. In summary, mastering state in functional components is essential for creating dynamic React applications. From simple counts to managing user information within forms, understanding the **state** hook opens up a world of possibilities. Start practicing with small components, gradually integrating more complex logic as you gain confidence. Who knows, you might just end up creating the next big hit application with these skills. Remember, the only limit is your imagination and willingness to experiment. Happy coding, and I can't wait to see what you create with state management. It's great that we can establish a state persistent within a function component. Managing multiple states and handling value changes as they occur is fundamental to creating interactive applications with React. In this lesson, we will dive deep into how to manage multiple states effectively, ensuring our applications remain responsive and user-friendly. So far, we learned about managing state within functional components in React using the **state** hook, which allows for creating interactive and dynamic applications. We explored how to manage local state, handle multiple pieces of state in a single object, implement conditional rendering, and reset state after form submission. Understanding the importance of keeping state minimal and avoiding complexity is crucial for effective state management. With these skills, you can enhance user experiences and build robust applications. Now we will cover how to support multiple states and manage value changes effectively within our components. Next, we will implement a user form that captures first name, last name, and email using a single state object called formData. This state is maintained with Usestate, initialized with empty strings for each field. By doing this, we streamline our state management and avoid using multiple state variables. Now let's take a look at the handle change function, which updates form data dynamically. As the user types in any of the input fields, handle change is triggered, destructuring the name and value from the event target. This allows us to spread the previous state and update the specific key corresponding to the input field being changed, ensuring all user inputs are accurately captured while keeping the existing data intact. Next, we'll add the handle submit function, which prevents the default form submission behavior. When the user submits the form, it logs the form data to the console and then resets the form by clearing all fields in the state, showcasing an efficient way to manage interactive form submissions in React. By structuring our code this way, we create a clean and organized component that effectively handles related data inputs. Now let's delve deeper into the handle change function. It's essential to know how this function operates because it's the backbone of managing state within our form. Each time an input field changes, the handle change function is triggered. Here is how it works. When an input event occurs, the event object E contains a target with the properties name and value. The name corresponds to the specific field like first name, last name, or email, and value is the content that the user has typed in. By destructuring these properties from eTarget, we can make state updates efficient and maintain clarity in our code. Using the updata function of setFormData, we are taking the previous state prev state and spreading it into a new object, then using the bracket notation name to update the specific key within the state object with the new value. This way, we efficiently preserve any previously entered data while allowing the new input to overwrite the correct state field. As you can see, this technique is not just elegant, but also effective. Now let's implement the following enhancements to our user form component. In this version, we introduce a new state variable called submitted, which tracks whether the form has been successfully submitted. This allows us to provide immediate feedback to the user. When the user submits the form, the handle submit function is triggered. It prevents the default form submission action, sets the submitted state to true, and logs the form data to the console. Next, we reset the form data state to clear the input fields after submission, ensuring a clean slate for the next entry. In the UI, we conditionally render a thank you message that incorporates the user's first name. This not only personalizes the experience, but also confirms to the user that their submission was successful, enhancing the interactivity of the application. Additionally, by maintaining an organized state structure for form data, we streamline the process of managing and updating the form fields dynamically as the user inputs their information. This implementation effectively demonstrates how to utilize state for improved feedback and user experience in functional components. Now let's see how we can implement user input validation within our form. We start by introducing an error state to keep track of any validation messages that might arise during the form submission process. Inside the handle submit function, we begin by preventing the default form submission behavior. Then we check whether any of the fields, first name, last name, or email, are empty. If any field is left unfilled, we set an appropriate error message indicating that all fields are required and halt further processing. This is crucial as it ensures that users are guided to provide complete data before they can submit the form. If all fields are filled correctly, we proceed to set the submitted state to true, clear any existing error messages, and log the submitted data to the console for verification. After this, we reset the form fields to their initial empty state so that the form is ready for the next entry. Additionally, we include logic to conditionally render an error message in red text if there are validation issues, and provide a personalized thank you message upon successful data submission. This feedback mechanism greatly enhances user experience by preventing incomplete submissions and giving users clarity on their actions. Now let's take a look at how we can extend our form to accommodate multiple user submissions. In this implementation, we import React and utilize the Usestate hook to manage state across our component. We initialize 3 state variables: form data for capturing user input, useList to keep a history of submissions, and error to handle any validation messages. The handle change function dynamically updates the form data object as the user types in the input fields, ensuring that our component remains responsive. Upon form submission, the handle submit function validates the input fields. If any field is empty, it sets an error message. If validation passes, instead of simply logging the submission, we append the current form data to useList, effectively creating a record of all users who have submitted the form. This list is rendered as an unordered list in the component, showing all user entries. Through this setup, we not only manage individual form submissions, but also provide a clear display of multiple entries, enhancing the user experience by keeping a dynamic record of inputs. Given all these examples, it's clear how effectively we can handle multiple states in functional components, allowing for sophisticated interactions. We've seen how to dynamically handle state changes, validate inputs, maintain lists, and render conditional messages. While all this may sound daunting at first, understanding and practicing how to manage state effectively forms the backbone of high-quality React applications. Just remember, when managing state, keep it simple, organized, and close to its context. Avoid deep nesting and aim for modular code that can grow and evolve as your application does. The more you practice these patterns, the more instinctual they'll become. This knowledge of multiple states and values will prove invaluable as you continue to build interactive applications. It's not just about collecting data, but creating a responsive system that keeps users engaged and satisfied with dynamic feedback. Embrace these concepts, and you'll be well on your way to becoming a skilled React developer. Building single-page applications is an exciting topic that opens the door to a more fluid and dynamic user experience. Today, we will explore how to create a single-page application, commonly referred to as in SPA, using React. We'll focus on managing state effectively to switch between different views seamlessly. So far, we learned about managing multiple states within functional components using the *Usestate ** hook, enabling interactive applications. We explored utilizing a single state object to group related data, making our code more efficient and manageable. We also covered handling user input, validating it before submission, and maintaining a list of submitted data. By following these practices, we can create responsive and user-friendly applications that enhance user experiences. Now we will cover how to build a complete SPA, incorporating routing to navigate between different components without refreshing the entire page. Now let's see how we can implement the main app component of our single-page application. In this code, we first import React and the Usestate hook, which allows us to manage component state. We also import the nav, home, and product components to be included later. Inside the app component, we set up the selected page state using the Usestate hook, initializing it with the value, home. This means that when the application loads, the home page will be displayed by default. Next, we return the JSX structure, which consists of a div container. Within this container, we render the nav component and pass down the selected page state and a function to update it, setSelectedPage. This allows the navigation component to highlight the current page and change it when a user clicks on different menu items. We also have a placeholder for the routes component, where we'll handle the routing logic. This organization sets the foundation for a responsive app that can seamlessly switch between views based on the user's selection. Now let's take a look at the implementation of our nav component, which serves as the navigation interface for our application. In this component, we start by defining an array called menus, where each object represents a menu item with a unique key and a corresponding label. This structure allows us to map over the array and generate a button for each menu item dynamically. Next, we implement a return statement that renders a nav element containing the buttons. Each button is linked to an onClick event that triggers the onSelect function passed down from the parent app component, allowing the app to update the selected page state whenever a button is clicked. This interactivity enhances the user experience, as clicking a button immediately reflects the change in the application's view. Furthermore, we make use of the selected prop to conditionally apply styles to the buttons, ensuring that the active page is highlighted with bold text. This visual cue helps users easily identify which page they are currently on, contributing to a clearer navigation experience within our single-page application. Next, we will write the routes component to manage our application's routing logic. This component will determine which content to display based on the value of the selected prop passed down from the parent app component. Here, we utilize conditional rendering to check the state of selected. If it holds the string home, the home component is rendered. Conversely, if it equals product, the product component is displayed. This approach allows for a seamless transition between different views, enabling users to interact with the application without experiencing a full-page reload. It exemplifies the core principle of single-page applications, efficient navigation, and a fluid user experience. By leveraging simple JavaScript expressions within curly braces, we elegantly control the visibility of our components based on user choices. This showcases how React's flexibility makes it easy to build interactive UIs. As we implement this logic, we set the foundation for a responsive application that enhances user engagement and satisfaction, key pillars of modern web development. Now let's define our home and product components, which serve as the foundational elements of our application. First, we'll create the home component that simply returns a header, welcoming users to the home page. This basic structure allows us to focus on the functionality of our spa. We can always enhance it with additional content and styles later. Next, we will implement the product component, which similarly returns a header stating that this is the product page. Both components are straightforward, highlighting the simplicity of setting up components in React. They demonstrate how to create reusable components that can be rendered conditionally based on user interaction. This approach allows for flexibility in expanding functionality in the future. By keeping these components simple, we establish a clear starting point for adding more complex features as we develop our application further. After creating these components, we ensure to export them so they can be imported and utilized within other parts of our spa, such as in the routes component for dynamic rendering based on the selected page. Now we will implement the entry point of our application. To do this, we import React and React-DOM, which are essential for rendering our components. The app component acts as the central hub for our single-page application, encapsulating all the functionality we've built. We then utilize React-DOM render to mount the app component onto a specific element in our HTML file, identified by the root ID. This process essentially connects our React application to the DOM, allowing it to be displayed in the browser. Next, let's take a look at how we connect our components seamlessly. By ensuring that all components are correctly imported, we can maintain structure and organization within our application. This setup allows users to interact with our application via the navigation we established. When users click between the Home and Product buttons, they will observe that the content updates dynamically without a full page refresh. This behavior exemplifies the capabilities of single-page applications, providing a snappy and engaging user experience. We will begin by installing React Router to enhance routing capabilities in our single-page application, SPA. This involves executing the command npm install React Router DOM, which will add the necessary library to our project. React Router provides essential tools for effectively creating and managing routes. Following the installation, we will modify our app component to incorporate React Router. Within the updated app, we will encapsulate the application in a router, granting it routing capabilities. Additionally, we will utilize switch from React Router to ensure that only one route is active at a time, which is crucial for maintaining a tidy user interface. Each route will specify a particular path and link it with a corresponding component. For example, the route path / will render the home component, while the product path will present the product component. Finally, we will update the nav component to leverage React Router's link elements instead of buttons for navigation. This modification will enable users to move between pages without triggering a full application refresh, thereby preserving the single-page application experience. By selecting the links for home and product, users can transition between views seamlessly, illustrating the dynamic functionality of our application. Next, we will implement the nav component, which will enhance our application's navigation experience. In this updated version, we will use React Router's link component instead of buttons. The link component allows us to navigate to different routes without refreshing the page, preserving the single-page application SPA behavior. First, we import link from React Router DOM. Inside the nav component, we define a simple navigation structure with two links, one for the home page and another for the product page. Each link specifies the to-prop, which determines the path that will be accessed when a user clicks the link. By replacing buttons with link, users can seamlessly transition between pages, enhancing their overall experience as the app responds quickly without a full reload. This change not only simplifies the navigation, but also encourages best practices in SPA development, where components function together to create an engaging and fluid interface. Now, with this implementation, our users can enjoy a consistent user experience that aligns perfectly with modern web standards. So far, we've built a dynamic single-page application using React. We've managed state effectively, created navigation, and integrated routing with React Router. Next steps could include adding more components, managing more complex states, or even incorporating backend integration for data fetching. As we wrap up this lesson, remember that building SPAs is all about creating a seamless user experience. Don't hesitate to experiment with different components, routes, and styling to make your application unique and engaging. Thank you for joining me today. I hope you're excited about building single-page applications with React. Keep experimenting with your applications and push the boundaries of what you can create. Happy coding, and I'll see you. Let's dive into the fascinating world of state management in React applications. State management is a crucial concept in building interactive applications, enabling developers to handle dynamic data efficiently. Now that we have crafted a state, and also seen how flexible a state can be used to either make a new update or listen to a value change, let's get hands-on and apply what we have learned to an app. So far, we learned about building single-page applications, SPAs, using React, focusing on state management and seamless navigation. We created components including app, nav, home, and product, along with routing logic to display different views without page reloads. We enhanced our SPA by integrating React Router for more complex routing configurations and used the link component for better user navigation. Next, we will explore adding more components and features to our application. Now let's see how we can implement a simple counter application using the Usestate hook in React. We start by importing React and the Usestate hook, which is essential for adding state to our functional components. The counter component is defined next, where we initialize the state variable count to 0 and create a function, setCount, to update its value. Within the counter component, we have defined a function called increment, which will be triggered when the button is clicked. This function utilizes setCount to increase the value of count by 1. The JSX returned from the counter component contains a div that displays the current count and includes a button that, when clicked, will call the increment function. Every time the count state updates, React handles a re-render, ensuring the displayed count reflects the latest state. This simple example perfectly illustrates how the Usestate hook works to create interactive components, making it easy to manage and update state as user actions occur, leading to a dynamic user interface. Now let's see how we can enhance our increment functionality by using a functional update pattern with the setCount function. In this revised version of the increment function, we pass a callback to setCount, which takes the previous state value, prevCount, as its argument. This ensures that each time we trigger an increment, we reliably base the new state on the most up-to-date value of count. By using this approach, we mitigate the risks associated with synchronous state updates, which can sometimes lead to unreliable values if the state updates are not managed correctly. This technique becomes especially important in more complex applications where components interact and share state. Properly managing state updates in this manner will help you build more robust and predictable applications as you continue developing your project. Next, we will implement a more complex state management solution within our counter application by using a state object. This approach allows us to track not only the count, but also how many times the count has been increased or decreased. Now let's take a look at how we set up our state using the Usestate hook, initializing it with an object containing count, increments, and decrements. This structure makes it clear and organized, enabling us to manage related data more effectively. Then we define the increment function, which updates the state when the increment button is clicked. Using the functional form of setState, we access the previous state and ensure that we correctly increase the count and the number of increments. Similarly, the decrement function follows the same pattern, updating the count down and incrementing the decrements. Finally, we configure the return statement to display the current values of count, increments, and decrements within the interface, alongside buttons to control these actions. This approach illustrates the power of using state objects to manage multiple related pieces of data in a clean and efficient manner, enhancing both functionality and readability in our React application. Now let's see how you can implement a simple counter application that effectively shares state between multiple components. In this example, the app component acts as the common ancestor that holds the shared state, which is the count. The Usestate hook initializes the count at 0 and provides a way to update this value through the setCount function. Next, we define the increment and decrement functions, which allow us to change the count. The increment function increases the count by 1, while the decrement function decreases it. This encapsulation of state and functions within the app component demonstrates the concept of lifting state up, ensuring that both child components, count-to-display and count-to-controls, have access to the count value and the functions to modify it. The count-to-display component receives the current count as a prop and renders it within an H1 element, effectively reflecting the state. Meanwhile, the counter-controls component provides buttons that trigger the increment and decrement functions passed down as props, allowing for interactive state changes. This setup exemplifies a clear data flow and separation of concerns between components in a React application. Now let's implement the following code using React's Context API to manage the state of a simple counter application. We start by importing the necessary functions from React, such as createContext, useContext, and useState. Here, we create a new context named counterContext that will hold our counter state and associated functions. Next, we define the counterProvider component, which will manage the state of our counter. It initializes the count to 0 using the Usestate hook and provides increment and decrement functions to modify this state. By wrapping its children with counterContext provider, we make the counter state accessible to all nested components. In the app component, we utilize the counterProvider to encapsulate the counter-display and counter-controls components. The counter-display uses the useContext hook to retrieve the current count and display it, promoting a clean separation between display logic and data management. Meanwhile, counter-controls accesses the increment and decrement functions, allowing users to modify the count dynamically. This structure demonstrates effective state management and promotes scalability without prop drilling, providing a better architecture for larger applications. Now let's implement a performance optimization using React's Usememo hook in our counter application. In this example, we introduce a derived state that calculates the factorial of the current count. To start, we declare our main app component, where we manage a simple counter using the Usestate hook. This state holds the current count, initialized to 0. Next, we implement the factorial calculation inside the Usememo hook. Here, we define a function that recursively calculates the factorial of a number, ensuring that it returns 1 for values less than or equal to 0. By passing count as a dependency array to Usememo, we tell React to rerun the factorial calculation only when the count changes, thus preventing unnecessary recalculations on every render. This is particularly important for performance when dealing with expensive computations, as it allows our application to run more smoothly by avoiding repeated work. Finally, the JSX structure displays the current count and the computed factorial, alongside buttons to increment and decrement the count, providing an interactive experience. This approach highlights how React's hooks can significantly enhance application efficiency. As we conclude our journey through state management, it's clear that understanding and effectively utilizing state is vital for creating dynamic, responsive applications in React. We explored various techniques including the use of Usestate, updating state based on previous values, managing complex states with objects, lifting state up to share between components, and leveraging the Context API to avoid prop drilling. Additionally, performance optimizations with Usememo showed us how to handle heavy calculations efficiently. I hope this comprehensive dive into state management has provided you with valuable insights and practical skills to implement in your own projects. As you continue building your applications, remember that mastering state management will yield powerful results and enhance user experience. Happy coding, and I look forward to seeing all the amazing applications. React is powerful for building interactive user interfaces, yet one of its core principles often confuses beginners: state management. Understanding how state works is vital for any React developer. Today, we're diving deep into state management, what it is, why it matters, and how to effectively utilize it in your applications. So far, we covered the fundamentals of state management in React applications, emphasizing its importance for handling dynamic data and creating interactive user experiences. We explored how to use the Usestate hook for managing state and how to share state amongst components without the need for prop drilling through techniques like the Context API. We even touched on performance optimization with tools like Usememo to enhance efficiency. Now we'll deepen our understanding of how React treats state as a state machine and explore its implications in building efficient applications. Now let's implement a simple toggle button using the Usestate hook in React. The first step is to import React and the Usestate hook from the React library. We define a functional component called toggle button. Inside this component, we initialize our state variable, isToggled, which starts as false, along with a function, setToggle, for updating this state. Next, we create a handleToggle function that will change the state when the button is clicked. It utilizes a functional update to toggle the current state, flipping it from true to false or vice versa. This showcases how React manages state and updates the UI predictably. The component returns a button element, where the text displayed on the button changes dynamically based on the value of isToggled. If isToggled is true, the button shows on, and if it's false, it displays off. This straightforward example illustrates the essence of using state in React to control components based on user interactions, reinforcing your understanding of how state impacts the rendered output dynamically. Now let's implement a more complex component that demonstrates how to manage multiple states within a form using the Usestate hook. We'll define a userform component that manages user input for fields like username, email, and password. In this component, form data is initialized as an object that holds these fields, providing a structured way to manage related data. Next, we'll create a handleChange function that handles updates to the form fields. This function extracts the field's name and value from the event object and uses the setFormData function to update the corresponding field. By utilizing the spread operator, we ensure that the existing fields within form-data are preserved, only updating the specific field that has changed. This pattern simplifies state updates and avoids having to define separate handlers for each input field. Finally, the handleSubmit function will prevent the default form submission, allowing us to log the form data to the console instead. This demonstrates how we can collect and manage user input efficiently while keeping the code organized and maintainable. This approach not only enhances code readability, but also showcases React's powerful capability of handling complex states seamlessly. Next, we will write the following code to implement a user profile management system in React, demonstrating how to lift state up and share it among components. The user profile component serves as the parent, managing the user data state with the Usestate hook. This state holds the user's username and email, initialized as empty strings. It also features the updateUser function, which updates the user data state whenever called, using the spread operator to maintain existing values while merging in new data. Now let's take a look at how we pass this updateUser function down to the userform component. This child component handles input changes by calling updateUser with the appropriate field name and value, effectively allowing it to modify the shared state. After the form, the displayUser component is responsible for showing the current state of user data. It displays the username and email, ensuring that anytime the state changes, the displayed information is automatically updated. This setup exemplifies a clean and maintainable way to synchronize state among components in your React application. Now let's take a look at how to implement a simple theme switcher using React's Context API. First, we create a theme context using createContext, which will allow us to share the current theme, and a function to toggle it across components without the hassle of prop drilling. Next, we define our main app component where we utilize the Usestate hook to manage the theme state, initializing it with light. By wrapping our components within the theme context provider, we ensure that any child components can access the theme and the function to update it. Moving on, we have the toolbar component, which serves as a container for our theme button. This structure keeps our components organized and modular. In the theme button, we use the useContext hook to retrieve the theme and the setter function from theme context. This allows the button to display the current theme and toggle it between light and dark each time it is clicked. This approach effectively simplifies state management by leveraging the Context API, making our components cleaner and reducing the complexity associated with prop drilling. Next, we will implement the user profile component that effectively lifts the state of user data, allowing it to be shared between the userform and displayUser components. We begin by importing the necessary hooks from React, particularly Usestate for managing local state and useCallback to optimize performance. Inside the user profile, we declare user data state, initialized with empty username and email fields. Now let's take a look at the updateUser function, which is wrapped in useCallback. This ensures that the function reference remains stable unless its dependencies change, thus preventing unnecessary re-renders of child components that rely on it. This is crucial for maintaining performance in larger applications. In the return statement, we render the userform and displayUser components. The userform receives the updateUser function as a prop, allowing it to update the user data in the parent component whenever the form inputs change. Meanwhile, displayUser takes user data as a prop, dynamically reflecting any updates made through the form, ensuring that our application remains responsive and interactive. So we've covered the essentials of understanding state management in React. We started by discussing how React functions as a state machine and examined the importance of state management for building dynamic applications. We migrated from simple state with Usestate to more complex scenarios like managing a form and lifting state up to share between components. We navigated through the Context API as a solution to prop drilling, enabling state to be shared across the component tree seamlessly. Finally, we touched on optimizing performance with hooks like Usememo and useCallback, ensuring our applications run smoothly. I hope this deep dive has clarified the nuances of state management in React. It's a crucial skill for any developer hoping to build responsive and interactive web applications. With a solid grasp on these concepts, you can confidently tackle more complex React projects and focus on building enriched user experiences. Thanks for watching, and happy. Props are essential in React, serving as the bridge that allows data to flow from parent components to their children. Today, we will explore the interplay between props and state, understanding how they can work together to enhance the functionality and interactivity of our React applications. So far, we learned about state management in React, focusing on its role as a state machine that simplifies UI rendering based on state changes. We explored practical examples of using the Usestate hook, managing complex state in forms, and sharing state between components through lifting state up. Additionally, we discussed the Context API as a solution for prop drilling and how to enhance performance using Usememo and useCallback. This foundational knowledge equips developers to create dynamic and maintainable applications in React. Now we will delve into how props and state can collaborate effectively within components. Now let's see how we can implement the interaction between props and state in our components. In the parent component, we first declare a state variable called clickCount using the Usestate hook, initializing it to 0. This state will keep track of how many times the button has been clicked. We also define a function called handleClick that updates the clickCount state by incrementing its value each time the button is pressed. Next, we pass down two important pieces of information to the child component: the current clickCount formatted as a label and the handleClick function to be executed when the button is clicked. Inside the child component, we utilize these props to render a button, which dynamically displays the click count. This illustrates how the child component can both display data received via props and modify the parent state through a callback function. The close integration of props and state empowers our components, allowing for responsive user interactions and dynamic rendering based on updated state. Now let's see how we can implement state management in our parent component to handle click events and keep track of the number of times a button is clicked. We start by importing React and the Usestate hook, which allows us to create a state variable called clickCount initialized to 0. This clickCount will store our counter, while setClickCount will be the function we use to update this state. Next, we define a handleClick function that increments clickCount by 1 each time the button is clicked. This function utilizes the previous state value to ensure we accurately update the count. Within the return statement of our parent component, we render the child component, passing it a label prop that dynamically displays how many times the button has been clicked, formatted as a string. We also pass the handleClick function to the onClick prop of child component. In the child component, we receive these props and attach the onClick prop to a button element. This setup creates a seamless interaction. Each click updates the click count in the parent and consequently changes the label displayed in the button. This example illustrates the powerful synergy between props and state in developing interactive applications. Now let's implement the following code to demonstrate lifting state up in React. In this example, we create a parent component that manages a click count state, initialized to 0 using the Usestate hook. This state allows us to track how many times a button has been clicked. The handleIncrement function updates this count when called, and we also define a handleReset function to reset the count back to 0. Inside the return statement of parent component, we render two components, child component and reset button. The child component displays the current click count and accepts an onClick prop, which is linked to the handleIncrement function, enabling users to increase the count with each button click. Meanwhile, reset button allows users to reset the count by calling the handleReset function when clicked. Additionally, the child component accepts a label prop to dynamically display how many times it has been clicked, ensuring the user always sees up-to-date information. This approach exemplifies the concept of lifting state up, as both child components rely on the shared state managed within the parent, promoting clear data flow and synchronization. Now let's see how we can implement an example of improperly modifying props in a React component. In this code, we have a child component that receives a label prop from its parent. However, the implementation contains an error. It attempts to directly change the label prop by assigning it a new value, changed label. This approach is fundamentally incorrect, as props are meant to be immutable within the child component. Attempting to mutate them can lead to unpredictable behaviors and bugs in the application. To maintain a clear and predictable data flow, child components should not alter the props they receive. Instead, if the child component requires new information based on user interactions, it is crucial that the parent manages these updates, typically through callback functions that can change the parent's state. Thus, the parent would provide the necessary updates and re-render the child component appropriately, ensuring data integrity and reliability. This example serves as a reminder of the importance of respecting the immutability of props in React development. Now let's implement the following enhancements to our parent component to better manage multiple props. Instead of passing props like label and onClick individually to child component, we will create an object called childProps that groups these related properties together. By utilizing the spread operator, we can simplify the prop passing syntax. In the handleClick function, we update the click count state, which captures how many times the button has been clicked. This state is dynamically displayed in the button label, showing the user an interactive count. The childProps object encapsulates both the label and the click handler, which makes our component cleaner and easier to manage, especially as more props might be needed in the future. In the child component, we destructure the label and onClick props for clear access. This structure not only improves readability, but also enhances maintainability. By redefining our approach to passing props, we better align with React's best practices, demonstrating how props and state collaborate to create dynamic user interfaces. Now let's see how we can implement default props in our child component to create a more robust user experience. In this example, we define the child component so that it accepts a label prop, but we also provide a default value of default button. This means that if the parent component does not supply any label, the button will still render with the text, default button, instead of being empty or undefined. This approach is especially beneficial in scenarios where parents may inadvertently forget to pass props or when certain props are conditionally provided. By assigning a fallback value, we ensure that the component remains user-friendly and visually consistent, regardless of what values are passed in. Additionally, this technique emphasizes the importance of anticipating potential issues in user interfaces, reinforcing our commitment to creating resilient applications that always present meaningful content. Thus, utilizing default props not only enhances the functionality of our component, but also improves the overall experience for users interacting with our application. Next, we will write the following code to optimize our child component using Usememo. This high-order component is utilized to enhance performance by preventing unnecessary re-renders. When a component wrapped in Usememo receives the same props on subsequent renders, it skips the rendering process entirely, which can be beneficial for components that render frequently or deal with complex visuals. In this example, our child component accepts two props, label, which dictates the text displayed on the button, and onClick, a function that triggers upon button clicks. The console log statement, child rendered, within the component helps demonstrate when the component is actually being rendered. By adopting Usememo, we ensure that the child component only re-renders if its label or onClick props change, thus effectively managing component lifecycle and boosting overall application performance, especially as applications scale up in complexity. This approach illustrates a prudent strategy for optimizing React components without sacrificing functionality or user experience. In conclusion, combining props and state within your React components is a powerful method to create interactive applications. By effectively managing immutable props and mutable state, lifting state to maintain synchronization across components, and ensuring clear and efficient prop handling, you can build robust applications that provide stellar user experiences. Props serve as the data courier between components, while state maintains the current condition of your application, allowing you to respond dynamically to user interactions. Understanding how these concepts work together enables you to harness the full potential of React's component-based architecture. With the foundational knowledge of state management, the context API, and performance optimizations, you are now well equipped to tackle the challenges of developing dynamic and maintainable React applications. Understanding React hooks and state management. React has transformed the way we build user interfaces, making it more efficient to manage dynamic state in our components. Today, we're going to dive deep into the concept of React hooks and how they simplify state management, helping you write cleaner and more maintainable code. So far, we've learned about the importance of props in React as a means to pass data from parent to child components, while also exploring how state keeps track of dynamic data that changes over time. We discussed the concept of lifting state up to manage shared data between components and highlighted the significance of immutability in props. Furthermore, we examined how to manage multiple props through object destructuring, utilize default props for robustness, and optimize performance using techniques like Usememo. This foundational knowledge empowers us to build interactive and maintainable applications in React. Now, we will talk about React hooks, their purpose, and their relationship with state management. Next, we will write the following code to demonstrate the Usestate hook in action by creating a simple counter component. This component will utilize the Usestate function from React to manage a piece of state called count. Initially, the count is set to 0, and we leverage an array destructuring pattern that gives us both the current state value and a function to update that value, setCount. Within the component, we return a JSX structure that displays the current count value in a paragraph. This dynamic updating is facilitated by a button. When the button is clicked, it calls the setCount function, incrementing the count by 1 each time. This approach illustrates how React's state management allows components to re-render in response to user interactions seamlessly. Using hooks like Usestate simplifies state management significantly compared to class-based components, making our code cleaner and easier to understand. This pattern of state management not only makes our UI more interactive, but also promotes best practices in React development. Now let's see how we can implement a more complex state structure using the Usestate hook to manage a user profile. In this example, we create a single state object that holds both the user's name and age, encapsulating related data together. This approach simplifies state management by minimizing the number of Usestate calls, making the code cleaner and easier to maintain. Next, we define 2 functions, updateName and updateAge, which handle the input changes for the respective fields. These functions utilize the spread operator to create a new user object while preserving the existing state properties. This is critical because it maintains immutability, preventing direct modifications to the state, which could lead to unpredictable behavior in the component. As users type into the input fields, the corresponding update functions are triggered, updating the state accordingly. This allows the displayed information to reflect the current state instantly. Ultimately, this pattern showcases a more efficient way of handling multiple state variables by leveraging object structures, enhancing both readability and organization in your React components. Now let's dive into the implementation of a data fetching component using React's Useeffect and Usestate hooks. Here, we create a functional component called DataFetcher, where the initial piece of state holds an empty array for our data and a loading state set to true. Next, we utilize the Useeffect hook to manage side effects, specifically fetching data from an API when the component mounts. By passing an empty dependency array, we ensure that this effect runs only once, mimicking the behavior of component.didMount. Inside the effect, we define an asynchronous function, fetchData, to make an API call. After receiving the response, we pause it as JSON and update our data state with the fetched results while also switching the loading state to false. Before the rendered output, we check if the loading state is true. If so, a loading message is displayed to the user. Once the data is fetched, we map over the data array and render each item in a new div, using the item's unique id as a key. This implementation demonstrates how to effectively handle asynchronous data fetching and state management in functional components. Now let's implement a cleanup mechanism for managing subscriptions effectively in our component using the Useeffect hook. In this code, we begin by creating a functional component called subscriptionExample, where we initialize a piece of state, isOnline, to track the online status of the user. Next, we use the Useeffect hook to set up event listeners for the Windows online and offline events. These listeners will trigger a callback function that updates the isOnline state based on the user's connectivity status. This allows our component to respond in real time to changes in connectivity, providing an interactive experience for users. However, it's crucial to manage these event listeners properly to avoid memory leaks when the component unmounts. Thus, we include a cleanup function that removes the event listeners for online and offline events. By returning this cleanup function from Useeffect, we ensure that our component stays efficient and free from unnecessary overhead. Finally, we render a message to the user indicating whether they are currently online or offline, demonstrating the dynamic nature of state management in React. Now let's take a look at how to manage state conditionally in a functional component. Here, we are using the Usestate hook to create 2 pieces of state, state.A and state.B. Instead of placing hooks within conditional statements, we maintain a consistent calling order by calling them at the top level of the component. This prevents potential issues that can arise from React's rules regarding hooks. In this example, state A and state B are both initialized regardless of the value of Usevisible. This means that both state variables are created every time this component renders, preserving the integrity of hook ordering. Inside the render method, we conditionally display state A based on the Boolean value of Usevisible. If Usevisible is true, the component renders a paragraph containing the value of state A. If false, that paragraph does not render, but the state B paragraph will still be displayed. This ensures that our component maintains the correct state management while allowing for conditional rendering based on props, demonstrating a clean and effective way to handle state within React. Let's summarize what we've learned so far. We've explored how to manage component state using Usestate and seen how to execute side effects with Useeffect. We've also discussed the importance of adhering to the rules of hooks to prevent unexpected behavior in our applications. These concepts create a robust framework for building dynamic, interactive user interfaces that can evolve with user interactions and external data. Now it's time for you to experiment with these concepts. Build a small application using React hooks, play with various states, and utilize Useeffect to manage side effects. The more you practice, the more fluent you'll become in managing state and understanding the nuances of React's capabilities. In today's session, we're diving deep into understanding how to manage component state in React using the Usestate hook. State management is a fundamental part of building dynamic web applications, and knowing how to handle it efficiently will significantly enhance the user experience. So far, we learned about the fundamentals of React hooks, emphasizing how they simplify state management and enhance code readability compared to class components. We explored the Usestate hook for managing component state and the Useeffect hook for handling side effects like data fetching and subscriptions. Additionally, we discussed key practices like maintaining the order of hooks to avoid unexpected behavior. This foundational knowledge equips us to build dynamic, interactive applications in React effectively. Now, we will cover in detail how the Usestate hook works, along with practical examples to illustrate its usage. Now let's implement a simple counter application using the Usestate hook. In the counter component, we begin by importing the necessary React library and the Usestate hook. We initialize a state variable called count and its corresponding update function, setCount, using Usestate with an initial value of 0. Next, we set up the component's return statement, which contains the user interface. Here, we display the current count value inside an h1 element. To provide user interactivity, we include two buttons, one for incrementing the count and another for decrementing it. Each button has an on-click event handler that calls setCount. When you click the increment button, it updates the state by adding 1 to the current count, while the decrement button subtracts 1. This functionality showcases how the state changes dynamically in response to user actions, making the application interactive. Not only does this example illustrate the basics of state management in React, but it also highlights the ease with which functional components can be made responsive and engaging. Now let's see how we can implement a counter using the Usestate hook in React. In this example, we define a functional component called counter, where we initialize the state variable count with a default value of 0 using the Usestate hook. The setCount function, which is a state updater, allows us to modify the value of count. Inside the component's return statement, we render a div containing an h1 element that displays the current count value. Next, we set up two buttons, one for incrementing the count and another for decrementing it. When the increment button is clicked, we call setCount, passing in a function that takes the previous count as an argument, prevCount, and adds 1 to it. This approach ensures that we always use the most up-to-date count value, which is particularly important for handling multiple updates that may occur in quick succession. Similarly, when we click the decrement button, we reduce the count by 1 in the same manner. This use of the functional update form helps avoid potential bugs related to stale closures while maintaining a responsive user interface. Now let's implement a simple to-do list application using the Usestate hook to manage our to-dos. First, we create a functional component called to-do list. Inside this component, we initialize two pieces of state, to-dos, which holds our array of to-do items, and input value, which controls the user input for adding new to-dos. Next, we define the add to-do function. This function is triggered when the user clicks the add to-do button. It checks if the input value is not just whitespace before adding it to the to-dos array. By using the spread operator, we maintain the previous to-dos while appending the new item, and then clear the input field for the next entry. We also need to handle removing to-do items efficiently. The remove to-do function filters out the selected to-do based on its index and sets the new array state, ensuring we do not mutate the original state directly, which is a best practice in React. In the rendered output, we have an input field for entering new to-dos, a button to add them, and a list displaying all current to-dos with a corresponding remove button for each. This interaction provides a functional and responsive user experience. Now let's take a look at how to manage an object state in a React component using the Usestate hook. In this example, we create a user profile component where we initialize the state with an object containing name and email properties set to empty strings. This structure allows us to manage user information effectively. Next, we'll implement a handle change function that dynamically updates the state when the user modifies the input fields. By leveraging destructuring, we extract name and value from the event target, which correspond to the input field name and its new value. Rather than repeating code for each input, we utilize computed property names. This means we can reference name within square brackets to dynamically set the appropriate property on our user object while maintaining the other properties intact. In our return statement, we render input fields for both name and email, ensuring they're wired correctly with the user state. The change events handler calls handle change, ensuring that user inputs are immediately reflected in the UI. Finally, we display the current user information, showcasing how state management can keep our interface aligned with user actions effortlessly. As we navigate through state management in React, it's crucial to remember some best practices. For instance, you should keep the state minimal, only store what's necessary. If derived values can be computed from other state variables, it's better to compute them in a render or use memoization techniques. Additionally, grouping related state, like in the user profile example, leads to a more organized state management strategy. This way, you can efficiently update the state as one object instead of managing multiple states. Speaking of organization, managing state can become increasingly complex as your applications grow. React Context and Redux are libraries you can utilize to handle global state in a more organized way, and they become especially necessary in larger applications. Our focus today is primarily on local component state with Usestate, but knowing these tools is essential for building scalable applications. Before we conclude, it's important to highlight how the Usestate hook interacts with component lifecycle. React's rendering cycle means that when state updates occur, the component re-renders to reflect the new state. Understanding this lifecycle helps in predicting how state changes affect the UI, allowing for smoother transitions and updates, particularly when combined with animations or complex UI interactions. This brings us back to where we started. The Usestate hook is not just about handling numbers or text, it's about managing the dynamic shifts in your application state, ensuring your UI responds in real time to user interactions, enhancing the overall user experience. So to summarize what we learned today, the Usestate hook simplifies state management in functional components, allowing for dynamic and interactive UIs. We covered how to declare state, update it based on previous values, and handle arrays and objects gracefully. Understanding these principles of state management equips you to build robust React applications. Remember, the key to mastering React isn't just knowing the APIs, but understanding how state management impacts your component's lifecycle and user interactions. Continue practicing with small apps, and soon you'll be able to create complex, interactive experiences with ease. Thank you for joining me in this exploration of component state management with React. Keep coding, and see you in the next. Now let's dive into understanding the Useeffect hook in React, a powerful tool that significantly enhances the behavior of functional components. This hook allows developers to synchronize a component with external systems, such as APIs or even timers, making your applications more dynamic and responsive. So far, we learned about managing component state in React using the Usestate hook, which helps create dynamic and interactive applications. We explored declaring state variables, updating them based on previous values, and managing arrays and objects effectively. Additionally, we discussed best practices for state management and how it interacts with the component lifecycle. This foundational knowledge positions us to build robust and responsive React applications. Now we will cover what Useeffect is, how to use it, its common patterns, and potential pitfalls you might encounter while using it. Next, we will write the following code to demonstrate how to use the Useeffect hook for managing side effects in functional components. This example illustrates fetching user data from an API when the component mounts. In this implementation, we begin by importing the necessary hooks from React, specifically Useeffect and Usestate. Within our user profile component, we define a state variable user to hold the fetched user data, initialized to null. Now let's take a look at the Useeffect hook. we use it to fetch data from https://API example.com/user as soon as the component mounts. The function passed to Useeffect will execute this API call, parse the response as JSON, and then update the user state with the retrieved data using setUser. Notice the second argument passed to Useeffect is an empty array, which indicates that this effect should only run once, mimicking the behavior of component.didMount. While the data is being fetched, we can render a loading message, and once the data is successfully retrieved, we update our state and render the user's information. This pattern effectively synchronizes our component's UI with the data from the external API. Now let's see how we can implement a user profile component that fetches data from an API when it mounts. In this example, we start by importing the necessary hooks from React, Useeffect for handling side effects and Usestate for managing the component's state. We create a functional component called userProfile, where we use Usestate to define a state variable user, initialized to null. Next, we set up Useeffect to run when the component first mounts. Within this effect, we utilize the fetch function to request user data from a placeholder API. Once the response is received, we convert it to JSON and update our user state using the setUser function, which triggers a re-render of the component. While the data is still loading, we conditionally render a loading message to improve user experience. As soon as the data is fetched and the state is updated, we display the user's name and email. This illustrates how to effectively use Useeffect for data fetching and how it interacts with React's rendering lifecycle. Now let's take a look at how we can refetch user data every time the user ID changes using the Useeffect hook. In the code, we define a functional component called userProfile, which accepts a prop called userid. Here, we manage the user data by utilizing the useState hook to set an initial user state to null. Next, we implement the Useeffect hook to perform our side effect, fetching user data from an API. By passing a template literal to the fetch function, we dynamically construct the API endpoint using the userid prop. This way, every time the user changes, the effect triggers a new fetch request to retrieve the corresponding user data. To optimize the fetching process, we include userid in the dependency array of Useeffect. This approach ensures that the effect only reruns when the userid changes, allowing us to respond effectively to user interactions or navigate to different user profiles seamlessly. Lastly, while the data is being fetched, we conditionally render a loading message. Once the user data is retrieved and set in state, the component re-renders to display the user's name and email, thereby ensuring our application remains responsive and dynamic. Now let's implement a timer using the Useeffect hook, which not only updates the count every second, but also ensures proper cleanup to avoid memory leaks. The component begins by setting up a state variable, count, initialized to 0. When the component mounts, the Useeffect hook sets up an interval that increments the count by 1 every second using the setInterval function. It's crucial to handle the cleanup to prevent the timer from continuing to run after the component has unmounted. This is achieved by returning a cleanup function from the Useeffect, which utilizes clearIntervalTimer to stop the timer effectively. By passing an empty dependency array as the second argument to Useeffect, we ensure that this effect runs only once when the component first mounts, making it an efficient setup for a basic timer. Finally, the component renders the current count in a div, providing real-time feedback on the counting process. This example illustrates the power of Useeffect for managing side effects, such as timers, while emphasizing the importance of cleanup to maintain optimal performance in a React application. Now let's see how we can implement a component that logs the value of a count state variable every time it changes. In this example, we start by defining a functional component called countLogger, which utilizes the useState hook to create a count state variable initialized to 0. Next, we introduce the Useeffect hook to handle side effects. Specifically, we want to log the current count to the console. Initially, we mistakenly use an empty dependency array, meaning the logging functionality will execute only once when the component mounts, failing to capture updates to the count as the button is clicked. To rectify this, we realize that we need to include count in the dependency array. With this adjustment, the Useeffect will now rerun every time count changes, providing updated logs with each increment of the count. This highlights a key takeaway. Always include necessary variables in the dependency array to ensure your effects respond to the current state, avoiding potential pitfalls in application behavior. Now let's take a look at an example demonstrating how improper use of the Useeffect hook can lead to infinite loops in React. In this code, we define a functional component called infiniteLoopExample, which initializes a state variable count to 0 using the useState hook. The Useeffect hook is then used to increment count each time the component renders. However, since count is included in its own dependency array, every time count updates, it triggers the effect to run again, leading to a continuous and never-ending loop that eventually crashes the application. To prevent this infinite loop, we can refine our Useeffect hook by implementing a condition that checks whether count is less than 10 before updating it. With this adjustment, the effect will only run to increment the count a maximum of 10 times, effectively breaking the loop and introducing a stopping condition. This illustrates the importance of careful dependency management within the Useeffect hook to avoid unintended outcomes while handling component state. By imposing such conditions, we can ensure that our application remains stable and performs as expected. As we continue to learn about effects, remember the principle of keeping everything in sync. If your effect depends on a state or prop, it should be declared in the dependency array. React provides tools like the ESLint plugin React hooks to help catch missing dependencies, ensuring a smooth development experience. In conclusion, the Useeffect hook is an indispensable part of building React applications. It replaces the more cumbersome lifecycle methods in class components with a simpler and more intuitive API. By using this hook effectively, you can perform operations that directly interact with external systems and ensure your component state stays fresh and relevant. With practice, leveraging Useeffect for various scenarios, from data fetching to cleaning up subscriptions, will become second nature. So as you continue your journey with React, always experiment with the Useeffect hook. It not only powers interactive components, but also enhances your application's responsiveness and efficiency. The Useeffect hook is a powerful feature in React that allows functional components to handle side effects effectively. Understanding how to utilize Useeffect can significantly enhance your React applications by making them more dynamic and responsive to changes. Let's dive deeper into what the Useeffect hook does, how to use it properly, and some common patterns and practices. Now let's take a look at how we can implement a simple data fetching functionality in our React component using the Useeffect hook. In this code, we define a functional component named DataFetcher, where we initialize two pieces of state, data for storing the fetched posts and loading, which is initially set to true to indicate that data is being loaded. Inside the Useeffect hook, we make a fetch call to an API endpoint, specifically retrieving posts from a placeholder API. When the data is successfully fetched and converted to JSON, we update the data state with the received information and set loading to false, indicating that the data is ready to be displayed. It's important to note that we provide an empty dependency array as the second argument to Useeffect, ensuring that this effect runs only once when the component mounts, similar to the component-did-mount lifecycle method in class components. Next, we conditionally render the component's output based on the loading state. If loading is true, we display a loading message. Otherwise, we map through the data array to render each post's title as a list item. This structure ensures that our user interface efficiently reflects the data fetching process. Next, we will write a countOnTimer component that demonstrates how to use the Useeffect hook to manage side effects, specifically for setting up a timer. In this example, we start by importing React and the Useeffect and Usestate hooks from the React library. We declare a state variable named count, initializing it to 10 using Usestate. Now let's implement the Useeffect hook, which is responsible for creating an interval timer by using the setInterval function. This function decreases the count state every second, but only if count is more than 0. Importantly, we also return a cleanup function that clears the interval when the component unmounts or before the effect runs again. This prevents memory leaks by ensuring that the timer stops running when the component is no longer on the screen. Finally, the rendered output displays the current countdown, allowing users to see the timer update dynamically. This implementation illustrates a common pattern for using side effects in functional components to enhance user experience. Now let's see how we can implement a simple counter application using the Useeffect hook to manage state changes effectively. In this code, we define a functional component called counter, which manages two pieces of state, count, initialized to 0, and increment, initialized to 1. Within the Useeffect hook, we create a function called handleIncrement that updates the count state by adding the current increment value to it. By including increment in the dependency array, we ensure that this effect runs every time the increment state changes. This is crucial because it allows the count to be updated dynamically in response to user input without causing an infinite loop, which could occur if we failed to properly manage our dependencies. The component renders the current count value and provides a button that allows users to increase the increment value. With each click, the increment state is increased, triggering the effect to recalculate the count accordingly. This demonstrates effective use of React's state management and the Useeffect hook to respond to user interactions seamlessly. Now let's take a look at how to manage multiple side effects in a single React component using the Useeffect hook. In this example, we create a component named UserInfo, which is designed to handle two distinct side effects, fetching user data and monitoring the online-offline status of the application. To start, we use the Usestate hook to create two pieces of state: user data to store the fetched user information, and is online to track if the user is currently online. The first Useeffect runs when the component mounts, triggering an API call to fetch user data from a specified endpoint. Upon receiving a successful response, we update the user data state, which will later conditionally render the user's name or a loading message. Next, we implement a second Useeffect dedicated to tracking the online status of the user. We set up event listeners for the browser's online and offline events to update the isOnline state accordingly. Importantly, this effect includes a cleanup function to remove those event listeners, preventing potential memory leaks. This structured approach allows us to compartmentalize functionality, ensuring our component remains clean and efficient while effectively handling multiple side effects. Now let's implement the Debounced functionality for our API calls using the Useeffect hook. In this example, we initialize two pieces of state: query for the search term entered by the user and results to store the search results fetched from the API. The Useeffect hook is employed to manage the API request, which triggers whenever the query changes. Inside the Useeffect, we set a timeout that delays the API call by 300 milliseconds after the last input change. This debounced technique prevents making multiple requests on every keystroke, thereby improving performance and avoiding unnecessary server load. If the query is not an empty string, we proceed to fetch the search results from our API. The response is parsed as JSON, and the resulting data is then stored in the results state. Crucially, we also return a cleanup function that clears the timeout whenever the effect is re-executed, ensuring that only the latest request is completed. This mechanism allows us to maintain a smooth user experience, minimizing load times and enhancing efficiency by managing the frequency of our API requests properly. So far, we've captured incredible insights about the Useeffect hook, grasping its importance in managing side effects in React applications. We've learned how it can influence data fetching, event management, and how to optimize for performance. Now, let's wrap things up by discussing common mistakes developers make when using Useeffect and how we can avoid them. First and foremost, failing to declare all dependencies in the dependency array can lead to stale closures. This could mean that your effect does not have access to the latest state or props, resulting in unexpected behavior. Always ensure that you include every variable that your effect depends on. Another common mistake is performing asynchronous operations without proper error handling. Asynchronous code can often fail silently if not managed correctly. Always include a catch block to handle any potential errors gracefully. Finally, remember to always clean up side effects. If your effect creates any subscriptions, intervals, or other event listeners, make sure to clean them up to avoid memory leaks and unintended behavior. To recap, today we've detailed understanding the Useeffect hook, dissecting it into manageable segments that elucidate its role in handling side effects. We covered its syntax, how dependencies work, managing multiple effects within a component, performance optimization, and common pitfalls to watch out for. As you integrate what you've learned, you'll find Useeffect is not only powerful, but also versatile, capable of transforming your applications into smooth, user-centric experiences. By mastering the Useeffect hook, you're well on your way to building responsive applications that leverage the full power of React. Keep practicing these principles, and remember, every time you apply Useeffect, you're making your applications cleaner, faster, and more efficient. Understanding React performance optimization with Usememo is an essential skill for any React developer. In today's lesson, we will dive into how the Usememo hook can help improve the performance of your React applications. So far, we learned about the Useeffect hook in React, focusing on its role in handling side effects within functional components while managing dependencies effectively. We've discussed various use cases, such as data fetching, event management, and performance optimization, including debouncing API calls. Additionally, we highlighted common pitfalls, like missing dependencies and improper error handling, emphasizing the importance of cleanup to prevent memory leaks. Overall, we've established a foundational understanding that enhances our ability to build dynamic and responsive applications. Now we will cover Usememo, its purpose, and how it can be applied effectively in your projects. The Usememo hook is designed to memorize the output of a function and return the memoized result, which can significantly enhance the performance of functional components when used correctly. This is especially useful when you have computationally expensive calculations or when you want to prevent unnecessary re-renders of components. Essentially, Usememo allows developers to optimize performance by avoiding recalculations unless certain values change. The syntax is straightforward. Const memoized value Usememo equals compute expensive value a b. In this example, the function compute expensive value will only run when or b changes, preserving the previous result otherwise. Now let's implement a simple React component called numberList, which will allow us to filter through a list of numbers based on user input. We start by importing React along with the Usestate and Usememo hooks. The Usestate hook initializes the filter state, which will hold the current value of the input field. Next, we utilize the Usememo hook to optimize the filtering process. This hook memorizes the results of the filtering operation, recalculating the filtered numbers array only when the input filter changes or when the original numbers array changes. This prevents unnecessary recalculations and enhances performance, especially as the list of numbers grows. In the rendered output, we provide an input field for the user to type their filter string. The current filter state updates on every change in the input field. Below the input, we display a list of filtered numbers, mapping over the filtered numbers array to create a list item for each number. Using Usememo in this context makes our component responsive while maintaining optimal performance, demonstrating the effectiveness of this hook in practice. Now let's take a look at an example of how we can use the Usememo hook to optimize rendering a list of user profiles. The user profile list component takes a user's array as a prop and is responsible for rendering each user's profile efficiently. Inside the component, we utilize Usememo to memoize the list of rendered user profiles. By wrapping the mapping operation in Usememo, we ensure that the expensive operation of creating user profile elements only occurs when the user's array changes. This is crucial in applications where the user list may be updated frequently, as it helps prevent unnecessary recalculations and keeps the interface responsive. The result of this mapping is stored in the rendered user's constant, which is then returned inside a div element. This approach demonstrates how Usememo can preserve performance by saving the previous rendered output and skipping recomputation unless the relevant data changes. Consequently, this small optimization can lead to significant improvements in performance, especially in more complex applications with dynamic user data. Now let's take a look at how we can optimize our user profile component to enhance its performance. The user profile component is wrapped with React Memo, which is a higher-order component that prevents unnecessary re-renders. This means that the user profile will only re-render if its props, specifically the user prop, have changed. By using React Memo, we can ensure that any computationally intensive rendering logic within user profile is executed only when necessary, thus improving the overall performance of our application. Inside the component, we are handling potentially complex rendering, where we display username. By leveraging memoization, we eliminate redundant calculations, which is especially beneficial in scenarios where rendering logic is not trivial. This approach, fostering efficiency, aligns well with our goal to keep the application responsive, particularly when dealing with lists of user profiles. By using React Memo, in conjunction with the memoized values from Usememo, we can further fine-tune performance, ensuring a seamless user experience. This practical application demonstrates the power of combining memoization strategies in React applications. Next, we will implement a counter component to demonstrate how the useCallback hook can optimize function handling in our React application. In the counter component, we start by creating some state to keep track of the current count using the Usestate hook. The initial count is set to 0. Next, we define an increment function using the useCallback hook. This function updates the count by incrementing it by 1 each time the button is clicked. The important aspect here is that we pass an empty dependency array to useCallback, which means the same instance of the increment function will be used across all re-renders, as long as there are no dependencies changing. As a result, when the counter component re-renders, the button that triggers the increment action will not cause other components that depend on increment to re-render unnecessarily. This is a crucial optimization, especially in larger applications where performance can be impacted by frequent re-renders. To conclude, this example of utilizing useCallback helps maintain optimal performance while managing state effectively. Before we wrap things up, it's also good to mention some tips you should keep in mind when using Usememo. Firstly, remember to always specify the correct dependencies in the dependencies array. If you forget to add a dependency, React won't know when to recalculate the memoized value, which could lead to stale data and bugs. Similarly, adding too many dependencies can defeat the purpose of optimization, so it's crucial to find the right balance. Additionally, keep in mind that Usememo is not a substitute for all performance optimization techniques. Other strategies such as code splitting, lazy loading, and better state management approaches should also be considered when optimizing your applications. In conclusion, mastering the Usememo hook can save you from performance pitfalls in your React applications. It's a powerful tool that, when combined with other performance strategies like useCallback and memoized components, can lead to snappier, more responsive user experiences. So get out there and give Usememo a try in your projects. As you implement it, take note of where your performance bottlenecks are and how Usememo can help you mitigate those. With practice, you'll find the right balance between optimization and complexity, helping you build high-performance React applications that will wow your users. Thank you for joining this lesson on React performance optimization with the Usememo hook in React is a powerful tool for optimizing performance by memoizing values. It allows developers to avoid unnecessary calculations on every render, making it essential for applications that handle complex data or perform heavy computations. Now let's see how we can implement a simple factorial calculator using the Usememo hook in React. First, we import the necessary modules, React and Usestate, Usememo from React. We define a functional component called factorial calculator, where we initialize a state variable number that defaults to 1. This will hold the user input for which we want to calculate the factorial. Next, we utilize the Usememo hook to memoize the factorial calculation. Inside the Usememo, we create a helper function, calculate factorial, that recursively computes the factorial based on the current number. The magic of Usememo lies in its dependencies. By passing number, we ensure that the factorial only recalculates when the user changes the input. This prevents unnecessary recalculations and enhances the performance, especially for larger numbers where factorial computation can be resource-intensive. In the return statement, we render an input field for user input and display the computed factorial. Whenever the number state updates through the input change event, the displayed factorial also updates seamlessly, showcasing the power of memoization in optimizing performance while providing responsive feedback in the user interface. Now let's see how we can implement a simple name filtering feature using the Usememo hook in our React application. In this example, we begin by importing the necessary React hooks, Usestate and Usememo. The component maintains a state variable called searchTerm, which is updated as the user types in the input field. We also define an array of names that we want to filter through. Next, we utilize the Usememo hook to optimize the filtering process. The hook takes a function that filters the names array based on the search term. It checks if each name, converted to lowercase, includes the lowercase version of the search term. This filtering computation will only rerun when either search term or names changes, effectively memoizing the filtered results. This approach prevents unnecessary calculations on every keystroke and enhances performance. Finally, we render an input field for users to type their search queries and a list of filtered names displayed as a list. The Usememo hook ensures that when the user types the same search term multiple times, the cached filtered array is returned immediately, improving the app's efficiency. Now let's take a look at an example that highlights the importance of dependencies in the Usememo hook. In the provided code, we have a functional component called counter, where two state variables, count and value, are defined using the Usestate hook. The computed value is created using the Usememo hook, which is designed to perform a calculation only when its dependencies change. However, in this instance, an empty dependency array is passed, meaning that computed value will only compute once during the initial render and will not reflect any subsequent changes to either count or value. As users interact with the buttons to increment count or value, they may expect the computed value to update accordingly. However, due to the incorrect dependency management, the displayed computed value remains static, leading to potential confusion and unexpected behaviors within the application. This example serves as a crucial lesson on the necessity of specifying the correct dependencies. When using Usememo, we must ensure that all variables affecting the computation are included in the dependency array to avoid performance pitfalls and stale data. Next, we will write a React component that effectively utilizes both the Usememo and useCallback hooks to optimize performance. First, we import the necessary hooks from React and set up the state for count and value. useCallback is employed to create a memoized function, incrementCount, which updates the count state. This function will remain the same across renders unless its dependencies change, which in this case there are none, ensuring it is not recreated unnecessarily. Now let's see how we can utilize Usememo to derive computed value, which represents the sum of count and value. This computed value will only recalculate when either count or value changes, preventing redundant calculations on every render. This optimization is crucial, particularly as our component grows in complexity or when the calculations involved are expensive. In the render method, we display both count and value alongside the computed value. We also provide buttons to increment count and value. This setup ensures our component remains performant by leveraging memoization, ultimately enhancing user experience with snappy updates and reduced rendering overhead. Let's not overlook best practices for using Usememo. Firstly, remember that not every computed value needs to be memoized. If a value is inexpensive to compute or doesn't cause performance issues, memoizing it may actually create more overhead and complexity than it's worth. A good rule of thumb is to use Usememo for costly calculations and lists that require filtering or mapping. Secondly, always ensure that dependency arrays are filled correctly to avoid stale or incorrect data. Mismanaging dependencies can cost you the performance gains that Usememo is supposed to provide. Lastly, always test and measure performance using React's built-in profiler or browser developer tools to see the effects of your optimizations. This will help you validate that your implementations are genuinely improving performance rather than adding unnecessary complexity. So far, we have learned about the power of the Usememo hook for optimizing React performance through memoization. We delved into how it can enhance rendering speeds by storing calculated results, examined practical examples such as filtering arrays, and discussed the relationship between Usememo and UseCallback. We also touched on the management of dependencies and best practices for effective use. Now let's explore the potential pitfalls of over-optimizing your apps with Usememo. In the grand scheme of things, overuse of memoization can lead to an increase in the complexity of your codebase. Sometimes, maintaining state in simpler terms without deep optimization is a better path, especially in small applications or components where performance is not impacted significantly. Like any optimization technique, it's key to use it mindfully and gauge whether it aligns with your application's needs. In summary, Usememo is an essential tool for React developers aiming to build efficient applications. By reducing needless recalculations of values during renders, it assists in keeping your app snappy and responsive. Just remember to balance your use of this hook with the need for maintainable and understandable code, ensuring you're not trading speed for clarity. Now go ahead, test out the Usememo hook in your applications and see how it can make your component performance shine. The Usememo hook in React is a powerful tool for optimizing search performance and enhancing user experience, especially when dealing with expensive computations. By using Usememo correctly, we can improve our application's responsiveness, ensuring efficient rendering and a smoother experience for users. Now let's see how we can implement an optimized name search functionality using React and the Usememo hook. We begin by creating a functional component called nameSearch, which accepts a list of names as a prop to filter through. Within this component, we initialize a piece of state called searchTerm using the Usestate hook, which will store the user's input from the search box. Next, we employ the Usememo hook to memoize the filtered results. This optimization means that the filtering operation will only re-execute when the search term or the names list changes. With this approach, we ensure that our application remains responsive as it prevents unnecessary calculations on every render. The filtering logic itself checks if each name includes the current search term, converting both to lowercase to make the search case-insensitive. Finally, we render an input field for capturing the user's input and display the filtered names in a list. As the user types, the search term updates, triggering the re-evaluation of the memoized filtering only when necessary, thereby improving performance and enhancing user experience in scenarios with large datasets. Benefits of using Usememo for search performance can be significant, especially as the size of the dataset increases. To illustrate, let's say our list of names grows to thousands of entries. Without memoization, each character typed in the input would cause the component to refilter the entire list, which could lead to noticeable slowdowns. When we use Usememo, the filtered result is cached, and if the search term hasn't changed, React will just return the cached result without recalculating it. You might be wondering about the dependencies we included in the Usememo hook. Managing dependencies is critical because failing to include everything that affects the memoized value can lead to stale or incorrect data. Remember, in this case, if the original list of names changes, perhaps fetched from an API, we need the filter to reevaluate. This is why both search term and names are included in the dependency array. Now, while Usememo is excellent for performance optimization, we should use it carefully. Misusing Usememo can lead to more confusion in our code without any real performance gains. It's important to measure whether the optimization delivers benefits before adding complexity. For example, if your filtering logic is quick and the number of items in your dataset is relatively low, you might see very little difference in performance with or without Usememo. In such cases, sticking with straightforward readable code is often more beneficial. But for larger datasets or more complex calculations, the use of Usememo shines. Another aspect to consider is how the Usememo hook integrates with React's re-rendering behavior. Each time the state updates, any component that uses the search term will re-render. However, because we've memoized our filtered results, the computationally intensive part, the filtering logic in our case, only occurs when necessary. This leads to improved performance and a snappier user experience, which is a win-win. Now let's implement a more complex version of our name search feature that includes pagination. In this component, we start by managing two pieces of state: search term, which captures the user's input in the search box, and current page, which keeps track of the current page of results being displayed. We set a limit on the number of results per page with the results per page variable. Next, we use the Usememo hook to efficiently filter the names based on the user's search term. This memoization allows us to avoid unnecessary recalculations unless either the search term or the list of names changes. Following that, we derive the paginated names by slicing the filtered names, ensuring that only the results for the current page are displayed. The total number of pages is calculated based on the length of the filtered results. In the render method, we create an input for the search term, a list for displaying the paginated names, and a series of buttons that allow the user to navigate between pages. By leveraging Usememo for both filtering and pagination, we optimize performance, particularly as the dataset grows. In summary, the Usememo hook is a vital piece in the optimization toolkit for React developers, especially when dealing with search functionalities. We've explored how Usememo aids performance by caching the results of computations and ensuring that complex calculations are only rerun when necessary. We've examined practical examples such as filtering search results and introduced advanced concepts like pagination while retaining optimization with Usememo. As a takeaway, remember that Usememo isn't a magic bullet. It's crucial to assess when its use is warranted. Always prioritize clarity and simplicity in your code, augmenting it with performance enhancements only when the situation truly calls for it. By applying these practices, you'll not only write more efficient React applications, but also provide a better experience for your users. To wrap up, if you're excited about digging deeper into React and performance optimization techniques, stay tuned. Up next, we'll be exploring the useCallback hook to further improve performance in our functional components. Just like Usememo is used for memoizing computations, useCallback allows us to memoize functions, which can help us treat performance concerns in a different yet equally important manner. So stick around, and let's level up our React skills. Now let's implement the theme context and theme provider to manage our application's theme state. We start by importing React, along with the create context and Usestate hooks that will enable us to create a context and manage state respectively. The theme context is initialized using create context, which allows us to provide and consume shared values efficiently. Next, we define the theme provider functional component. Inside this provider, we set up a state variable, theme, initialized to light, and a function set theme to update it. A helper function, toggle theme, is created to switch between light and dark modes by checking the current theme and updating it accordingly. This encapsulated logic supports our application by allowing any nested component to be notified of state changes without cumbersome prop drilling. Finally, we utilize the theme context provider to wrap the child components with our context value, which includes both the current theme and the toggle function. This structure not only provides an easy way to access and modify the theme state, but also signifies how context streamlines state management across an application's component tree, making it clean and efficient. Now let's implement the theme provider in our application through the app component. We start by importing React, the theme provider, from our theme context and the theme component. In the app component, we wrap the theme component with the theme provider. This structure ensures that any component nested inside theme provider can access the context, thus allowing them to read the current theme and toggle functionality seamlessly. Next, we will build out the theme component to demonstrate how it reacts to theme changes. Using the useContext hook, we draw in both the current theme and toggle theme function from the theme context. The component styling dynamically adjusts based on the theme value. For instance, the background and text colors change according to whether the theme is set to light or dark. This dynamic styling is achieved through a simple inline style object. Lastly, we include a button that, when clicked, triggers the toggle theme function, allowing users to switch between light and dark modes effortlessly, showcasing the power of context in managing state across our application. Now let's take a look at how we can expand our theme provider to manage not just the theme state, but also user information. In this updated implementation, we introduce a new state variable, user, which holds an object containing user details like name and email. The Usestate hook initializes this user state with default values. Next, we enhance the functionality of the theme provider by adding an updateUser function, which allows any component subscribing to the context to update the user data. This is particularly useful for scenarios where user information needs to be modified dynamically, such as changing the email address in a profile section. The theme provider now returns a context provider that shares both the theme state and the user state, along with their respective functions, toggle theme and updateUser, through the context. This means any nested components can easily access and use these values, making state management across the application seamless and efficient. By leveraging context like this, we significantly reduce the complexity associated with prop drilling and enhance the overall maintainability of our application. Now let's implement the user profile component, which is designed to display and allow the user to update their email address. This component utilizes the useContext hook to access context values from theme context, which encapsulates both user information and the updateUser function. The user profile component, we define a function called handleEmailChange, which listens for changes to the email input field. When the user types into the email field, this function is triggered, capturing the input's value and incorporating it into a new user object using the spread operator. This new user object is then passed to the updateUser function. This approach effectively updates the email in the context, ensuring that the change is propagated throughout the application. The rendered output of the component includes the user's name and an input field pre-filled with the current email. The input field is equipped with an onChange event handler linked to the handleEmailChange function, ensuring that any modification updates the context value seamlessly. This component thus enables real-time updates while maintaining a clean and efficient interface for managing user information. Now let's see how we can implement the user provider component to manage user-related state in our application. This component utilizes React's Usestate hook to create a state variable called user, which is initialized with a default object containing a name and email address. The component also defines an updateUser function, which updates the user state with new values when called. By wrapping its children in the user context provider, the user provider makes the user state and the updateUser function available to any components that consume this context. This means any component within the provider can access user information without needing to pass props through every level of the component tree. This is particularly beneficial for maintaining cleaner and more efficient code, especially in larger applications where prop drilling can become cumbersome. Next, we will juxtapose this with our existing theme provider, allowing us to manage both theme and user states separately, and demonstrate how they can work together to enhance our application's architecture by providing a clear separation of concerns. This way, each provider caters to specific data, optimizing performance and improving code clarity. Now let's see how we can implement a test for our theme component using Jest and React testing library. The test begins by importing the necessary functions from React testing library, along with the theme provider from our context file and the theme component itself. Within our test definition, we set up the environment by rendering the theme component wrapped inside the theme provider. This wrapping is crucial because it allows our test to simulate the actual context environment in which the component operates. Then, we proceed to assert that the rendered output includes the text corresponding to the light mode, specifically checking for the phrase light mode. This assertion verifies that our component correctly reflects the current theme state. By encapsulating theme component within the context provider in our test, we ensure that any logic depending on the theme context is appropriately exercised, thus making our test both reliable and meaningful. This testing approach not only confirms the basic functionality, but also sets the stage for scaling our tests to address more complex scenarios that depend on context. Managing user context in React applications is a pivotal aspect of building scalable and maintainable user interfaces. In this lesson, we'll delve into the intricacies of utilizing user context effectively, ensuring seamless integration of user information throughout your React app. So far, we've learned about managing state and updates in React using context, which allows us to share values between components without prop drilling. We've explored how to create a theme context to manage the application's theme dynamically, demonstrated through a theme provider and a theme component. Additionally, we saw how to expand our context to include user information and how to update this data efficiently. Finally, we discussed the importance of performance considerations when using context and touched on testing context-dependent components effectively. Now, we will cover how to specifically manage user context to streamline access, updates, and overall user experience. Now let's take a look at how to create the user context by defining the user context. We utilize React Create Context to establish this context, which allows us to hold and share user-related data across components in our application. By exporting this context, we make it accessible to any component that needs to consume user information, promoting a centralized data management approach. Next, we will implement the main app component where we set up our user management. Here, we use the Usestate hook to define the user state, which we initialize with initialuser. This state captures the user's information and a method to update it, which we encapsulate in a value object by wrapping our application with user context. Provider, we make this value available to all child components, facilitating seamless access to user information without passing props explicitly. By structuring our components this way, we enhance code maintainability and readability, ensuring that user states are easy to manage and update in response to user interactions across the application. Now let's see how we can implement the logo component to display the user's profile image and username. In this component, we begin by importing React and the useContext hook, which allows us to access our user data from the user context. We retrieve the user object directly from the context using useContext, user context, simplifying data access and reducing the need for prop drilling. The logo component then constructs a simple JSX structure that displays the user's avatar and their username. By rendering an image element with the source set to user, image URL, and a span containing user username, we ensure the UI reflects the current user's information. This approach is powerful because any change to the user object in the context automatically triggers a re-render of the logo component, keeping the interface in sync with the underlying state. This design pattern enhances maintainability and scalability in larger applications, enabling multiple components to share the same user context seamlessly. Thus, we achieve a clean component structure that significantly improves the overall user experience in our React application. Now let's take a look at how we can enhance the user interface by adding a logout functionality to the logo component. In this updated version, we first destructure user and change user from the user context, which allows us to access the user's information as well as the function to update that data. We extract the image URL and username from the user object for easy access. Next, we implement the onLogout function, which effectively clears the user information by calling changeUser with an empty object. This action is crucial as it resets the user state when the logout button is clicked. The return statement is where we render the component. If a username exists, we display the user's avatar along with their name and a logout button. This provides a seamless user experience. When the button is clicked, the UI updates instantaneously. However, if the username is not defined, we prompt the user to log in. This approach ensures that the context-driven updates reflect throughout the UI, maintaining a dynamic and responsive design. Now let's implement the login form component, which provides a simple way for users to log in. This component utilizes the useContext hook to access the user context, extracting the changeUser function that allows us to modify the user state. Within the component, we define a handle login function that simulates user authentication. Here, we create a user object with a predefined username and image URL, representing the logged-in user. Next, we specify a button that triggers the handle login function when clicked. This setup means that when the user clicks to log in as John Doe, the app captures that action, invokes changeUser with the created user object, and updates the context accordingly. The beauty of this approach lies in its simplicity and efficiency. Updating the context will automatically trigger a re-render of any components that rely on user information, such as the logo component. As a result, this seamless integration not only enhances the user experience, but also keeps the codebase organized and maintainable. Now let's take a look at how we can conditionally render different components based on a user's authentication status in our React application. In the app component, we utilize the Usestate hook to manage the user state, which holds information about the authenticated user. The value object combines both the user state and the changeUser function, allowing us to update user information contextually. Within the return statement, we wrap our UI in a user context provider, providing access to the current user context throughout the application. This is where we implement the conditional rendering logic. We check if the username property exists within the user state. If it does, we render the site component, which contains user-specific content. Conversely, if the username is absent, suggesting that no user is logged in, we display the login form component, prompting the user to enter their credentials. This approach ensures that only authenticated users can access certain sections of the application, thereby enhancing security and improving the overall user experience. As we wrap up our exploration of managing user context in React applications, it's crucial to understand the broader implications of using context wisely. Context not only reduces prop drilling, but also enhances the maintainability of the code by allowing centralized control over stateful data. By using context effectively, we enable components to respond to state changes dynamically, making the overall user experience smoother and more engaging. In this session, we covered creating user context, providing values through context, consuming data within components, and managing authentication states seamlessly. Emphasizing these principles can elevate your React application significantly. Thank you for joining me on this journey through managing user context. Now go ahead and implement these patterns in your projects for a more elegant and efficient user experience. To effectively contextualize user interfaces with React, it's vital to grasp the concept of context and how it allows for sharing information across various components within your application. Context serves as a powerful tool, especially when you want to share site-wide information or even specific details within a narrower scope without the hassle of prop drilling. This video will help you understand how you can leverage context to create organized user interfaces in a more efficient manner. Now let's implement the theme context, which is essential for managing user preferences regarding light and dark modes. We begin by creating a theme context using React Create Context, initializing it with a default mode set to light. This establishes a contextual environment where any component that subscribes to this context can easily access the current theme mode without passing props through each component level. Next, we will create a button component that utilizes the useContext hook to access the theme context. This allows the button to react to theme changes dynamically. Inside this component, we extract the current theme mode and use it to pass the mode as a prop to a styled button component, button style. The button style component is where the magic happens. It adjusts its text color based on the active theme. If the mode is light, it renders the text in black. Otherwise, it switches to white for better visibility in dark mode. This visual adjustment provides immediate feedback to users, enhancing their overall experience as they interact with different themes. Now let's see how we can propagate context changes across multiple components through a theme management system. In our app component, we wrap all child components, header, main content, and footer inside a theme context provider. This setup allows each child component to access the current theme via context, ensuring that any updates to the theme will automatically cascade down to all nested components. For instance, if a user opts to switch themes, all components utilizing this context will reflect the change instantly. Next, we will implement the header component, where we take advantage of the existing theme context. Here, we utilize the useContext hook to retrieve the theme and create a modified version of it by adjusting the primary color property. By using another theme context provider, we provide this updated theme only to the button component nested within the header. This demonstrates the flexibility of React's Context API, allowing specific components to override parts of the context without disrupting the global theme established at the app level. This approach contributes to a more organized and adaptable design for our user interface. Now let's dive into structuring our data for the customizable table. We begin by defining an array called fruits, where each fruit object contains a title and an optional status. This structure represents the data we'll be displaying within our table, showcasing various fruits and allowing for potential interactivity through the status indicator. Next, we will establish our base cell component, default cell. This component is designed to receive a value, prop, and simply render its contents inside a div. It serves as the fundamental building block for our table cells, enabling us to display text in a clean and straightforward manner. Now let's implement a more specialized cell with status cell. This component will accept a value prop as well and display different strings based on the Boolean status. By outputting either nice or OK, it highlights how we can extend our cell functionality, providing feedback based on the underlying data. This differentiation showcases the versatility of our approach, allowing us to tailor how each cell presents information based on its specific needs. Now let's take a look at how we can implement our table context. We start by creating a context using React's Create Context function, initializing it with an object that contains empty arrays for rows and columns, as well as an empty object for the current row. This context will serve as a shared data source for the components within our table, allowing them to access the necessary information without directly passing props through every level of the component tree. Next, we define the table component, where we will leverage the table context provider to encapsulate our table's rows and columns. Within this component, we create a value object that holds the columns and rows being passed as props. By wrapping the RowsMap method in the table context provider, we ensure that each table row component, which we will define next, has access to this contextual information. This setup allows each row to dynamically render its content based on the table's data structure, making our code cleaner and more maintainable. Now, with this context in place, each table row will be able to consume the context and adapt its functionality based on the shared data, leading to a more cohesive and intelligent interface for our table component. Now let's implement the following delete cell component, which demonstrates how users can remove a row from our table. This component leverages the table context to access the necessary data, including the current row and the collection of rows. By using the useContext hook, it pulls in the row, rows, and setRows values from the context. Next, we define a function called onClick, which is triggered when the user clicks the remove button. This function filters out the current row from the rows array, effectively removing it from the display. The setRows function is then called to update the state with the new set of rows, ensuring that the component reflects this change immediately. The component returns a simple button within a div labeled remove. When users interact with this button, they experience seamless interaction without the need for complex prop drilling, demonstrating the effectiveness of using context for managing state in a table setting. This approach simplifies the handling of components that need to perform operations on shared data, like deleting a row, enhancing both usability and maintainability in our React application. Finally, the flexibility of context allows developers to construct highly reusable components that can independently determine how they function based on context, thus keeping code maintainable and clear. Although passing data via props is sometimes necessary, leveraging context for state management adds a lot of simplicity to your applications. Updated context automatically re-renders components that consume it, a feature that not only enhances performance, but also eases debugging. Now, as a quick recap, we've explored how to effectively utilize context for theming across your applications and how to apply it practically within specific components like tables. Each strategy ensures better state management and a more fluid user experience in your React apps. Thank you for joining this tutorial. In this lesson, we will dive deep into understanding refs in React, what they are, how to create them, and when you might want to use them. We are transitioning from managing state through context to another essential tool React offers that can enhance your component interactions and manipulations. So far, we covered how to effectively manage user information and theming across components using context. We established user context and theme context, allowing for seamless integration of user data and UI theme customizations. We also took a look at implementing a customizable table through table context to handle cell behaviors and interactions. These strategies demonstrate how context can streamline state management and facilitate dynamic components in our React applications. Now, let's talk about refs and their importance in React development. Now let's implement a simple input component using refs in React to focus on the input field when the component mounts. We start by importing necessary hooks from React, namely Useeffect and Useref. Inside our functional component, FocusInput, we utilize Useref to create a mutable reference object, InputRef, initialized to null. This ref will allow us to directly interact with the input DOM element. Next, we set up a Useeffect hook that runs after the component mounts. In this hook, we call the focus method on InputRef current, which holds a reference to the actual input element. As soon as the component mounts, the input field gains focus, enhancing the user experience without requiring additional state management. Finally, in the return statement, we render an input element and attach our InputRef to its ref attribute. This ensures that InputRef current points to the correct DOM node, allowing for direct manipulation. This approach demonstrates the convenience of using refs for direct DOM interactions, streamlining actions that would otherwise complicate component behavior. Now let's take a look at a more dynamic implementation of refs in action. We will create a component called Dynamic Inputs, which allows users to add multiple input fields seamlessly. Here, we start by utilizing the Usestate hook to maintain an array of input values. The critical aspect of our implementation is the InputRefs array created with Useref. This array keeps track of the individual input fields, allowing us to manipulate their focus without triggering unnecessary renders. When a new input is added through the Add Input button, the addInput function updates our state, appending an empty string to our inputs array. The Useeffect hook is employed to monitor changes to this array. Specifically, it checks if the last input element exists and applies focus to it. This approach ensures that whenever a user adds a new input, they are immediately positioned to enter data in that field. As we iterate over the inputs array to render our input fields, we bind each input's ref to its corresponding entry in inputrefs. This assignment is crucial for enabling direct access to each input's DOM element and simplifies managing their focus dynamically. In this setup, we efficiently create a user-friendly mechanism for adding inputs while harnessing the power of refs for seamless interactions. You can see that inputrefs doesn't change its reference on every render, allowing for persistent access to each DOM element. The array of refs grows as we add inputs, and whenever new inputs are loaded, we set focus on the most recent one. But let's take a step back and think about when it's appropriate to use refs. Refs should be utilized when you need to access DOM elements directly, for example when implementing animations, integrating third-party libraries that manipulate the DOM, or managing focus. However, keep in mind that using refs, when possible, should be limited as they break the declarative nature of React. Now let's implement a straightforward example that demonstrates how to trigger animations dynamically using refs in React. In this scenario, we create a component called Highlight Box that allows us to highlight a box when it is clicked. To achieve this, we utilize the Useref hook to create a reference to the box's DOM element. Within the component, we define a function called Highlight that uses the reference to access the current property of boxref. When the box is clicked, this function changes the background color of the box to yellow, creating a highlight effect. After 500 milliseconds, we reset the background color back to its original state. This approach showcases how refs enable direct manipulation of the DOM without causing unnecessary re-renders in React, thus maintaining performance efficiency. Additionally, the box is styled with a fixed width and height, and we set a light blue background color as the default appearance. Accompanying the box, there is a paragraph that instructs users to click the box to see it highlight. This simple yet effective interaction exemplifies the powerful capabilities of refs in enhancing user experience with animations. Now let's take a look at how to handle cleanup in React effects, especially when dealing with event listeners. In this example, we create a Useeffect hook that adds an event listener for the scroll event when the component mounts. The handleScroll function logs a message whenever the user scrolls the page. Next, we need to ensure that this event listener is properly removed when the component unmounts or when the effect runs again to avoid potential memory leaks. This is achieved by returning a cleanup function from the Useeffect callback. In the cleanup function, we call whenDiRemoveEventListener with the same event type and handler function to detach the listener. This practice not only keeps our component performance optimal, but also prevents unnecessary background processes from lingering when they are no longer needed. While this example does not directly illustrate the use of refs, it highlights the critical importance of managing side effects in React components, ensuring that resources are cleaned up appropriately as part of the component lifecycle. By adhering to this pattern, we create more efficient and reliable components. At this point, we have accumulated a solid understanding of how refs work in React, their advantages, and their practical applications. We've examined how to create refs, how to use them within effects for focusing inputs and handling multiple inputs dynamically, and how to interact with the DOM for various use cases like animations. Before we wrap up, remember to always consider the React philosophy of unidirectional data flow where appropriate, using state and props whenever possible. Refs are powerful, but may introduce complexity if used excessively or inappropriately. Striking a balance is key to writing clean, maintainable code. In conclusion, mastering refs will equip you with yet another tool in your React toolbox, unlocking more complex interactions and enhancing your application's responsiveness. Try incorporating refs into your own components, explore different use cases, and see how they can streamline DOM manipulations in your React projects. Next, we'll implement a simple functional component called FocusInput to demonstrate the use of the Useref hook in action. Here we begin by importing the necessary React hooks, Useeffect and Useref. Inside the FocusInput component, we create a ref named InputRef, initialized to null, which will later be assigned to our input element. Now let's see how we can leverage the Useeffect hook. This hook will fire after the component has mounted, allowing us to interact with the DOM safely. Inside the effect, we call Focus on InputRef current, which directly points to the input element. This step ensures that our input field receives focus as soon as the component loads, demonstrating the power of refs to manipulate DOM elements without causing additional re-renders. Finally, we return a simple input field linked to the inputref, utilizing the ref attribute. This connection allows for direct DOM access, showcasing how Useref provides a seamless way to manage focus and seamlessly enhances user experience in our React application. Now let's see how we can test our focus input component to ensure it behaves as expected when it mounts. In this test, we import necessary functions from the React testing library, specifically render and screen, as well as our focus input component. The test checks that the input field is focused right after the component is rendered. We start by rendering the focus input component within our test. Once rendered, we use screenGetByPlaceholderText to locate the input element by its placeholder string, ensuring that we have a reference to the right DOM node. Finally, we assert that the current active element in the document is the input element we just retrieved. This test confirms that our focus logic works correctly when the component mounts, demonstrating how to verify component behavior concerning user interaction and DOM manipulation. Next, we will examine how to track previous prop values within a component using Useref. In this approach, we develop the previous value component, which monitors the changes in its value prop. By utilizing Useref, we hold a mutable reference to the previous value of the prop, allowing us to update it without triggering re-renders. In the Useeffect hook, we update our ref with the current value whenever it changes, thus maintaining a history of the prop's evolution. In the rendering phase, we display both the current and previous values on the screen in a simple yet informative format, showcasing how Useref can be a powerful tool for state management without incurring the performance costs associated with re-renders. Now let's implement the following code to test our previous value component. This test is crucial as it verifies that the component correctly updates the previous value when the current value changes. We begin by rendering the component with an initial value of 1 using the render function from React testing library. It's important to check that the current value displays correctly. At this point, the previous value should be undefined, as no prior value has been set yet. Next, we utilize the re-render method to update the value prop to 2. After re-rendering, we need to confirm that the component reflects this change accurately. The expectation here is that the displayed current value should now be 2, and the previous value should show 1, demonstrating that our Useref implementation captures and retains the previous value across renders, without causing the component to re-render unnecessarily. This effectively illustrates how Useref enhances our component's functionality by maintaining mutable state efficiently in a React environment. Now let's take a look at a timer component that utilizes the Useref hook to manage a count that updates every second. This component begins by setting up state for the count and a ref to hold the interval ID. Within the Useeffect hook, we create an interval using setInterval, which increments the count every second and updates the state accordingly through setCount. This approach allows us to maintain a clean separation of concerns, with the interval management handled by Useref. It's essential to ensure that we clean up the interval when the component unmounts or re-renders. To achieve this, we return a cleanup function from the Useeffect, which calls clearInterval, preventing potential memory leaks and unintended behavior when the component is no longer in use. The rendered output is simply an H1 element displaying the current count, allowing users to see their increments in real time. Next, we will write a test to verify the functionality of our timer component. Using Jest's fake timers, we can simulate the passage of time, making it easy to assert that the count increments as expected within a controlled test environment. This ensures our timer works reliably as intended. Now let's take a look at how we can integrate the powerful D3.js library with our React application using the Useref hook. In this example, we create a functional component called D3chart. At the beginning of the component, we define a reference to an SVG element using Useref, which enables D3 to access this DOM node directly without interfering with React's rendering process. In the Useeffect hook, which executes after the component mounts, we use the D3 library to select the SVG element through the reference we created. Before drawing anything, we clear any existing content within the SVG, ensuring that we start with a clean slate each time the component renders. This is particularly important to avoid rendering duplicate elements. Next, we append a blue circle to the SVG, specifying its position and radius with attributes. This integration showcases how Useref serves as a bridge between React and external libraries like D3, allowing us to manipulate the DOM directly while maintaining the benefits of the React lifecycle. Now let's see how we can implement a simple test for our D3chart component. In this test, we begin by rendering the D3chart component using the render method from the React testing library. This method gives us access to the rendered output and enables us to interact with it in our test. After rendering, we query the container for the SVG's circle element using the querySelector method. This is important as it allows us to assert the existence and correctness of the circle that the D3 library draws. Next, we utilize assertions to confirm two critical points. First, we check that the circle element is present in the document, ensuring that our D3 chart's rendering has occurred successfully. Then, we verify the tag name of the circle, which should rightly be identified as circle. This dual assertion not only ensures that our integration works as intended, but also confirms that the interactive features introduced by D3 are correctly rendered within our React component, highlighting the seamless collaboration between React's rendering process and D3's DOM manipulation capabilities. As we wrap up this journey into testing and utilizing Useref, it's clear that this hook can enhance the way you manage DOM elements and mutable state in React. From focusing inputs and tracking previous values to managing intervals and integrating with libraries, Useref brings a lot to the table without the overhead of unnecessary re-renders. So as you build your React applications, consider these powerful capabilities and remember to use them judiciously, always mindful of React's philosophy regarding state and rendering. Now let's take a look at the title component, which is designed to fetch and display data from an API. Inside the component, we initialize a state variable called text using the Usestate hook, which will eventually hold the title fetched from the API. Next, we implement the Useeffect hook to handle the side effect of fetching data when the component mounts. Within this hook, we initiate a fetch request to obtain data from a specified API endpoint. The response is then converted to JSON format, from which we extract the title and update the text state using setText. This process ensures that once the data is successfully retrieved, it will be reflected in our component. However, we need to be cautious here. If the user navigates away before the data fetch completes, React may attempt to update the state of an unmounted component, potentially leading to memory leaks. To mitigate this risk, we will later integrate a ref to track the mounting status of the component, allowing us to verify if it is still mounted before updating the state. This pattern will help ensure that our application remains efficient and free from memory issues. Now let's see how we can implement a more robust version of our title component that efficiently handles potential memory leaks. In this updated code, we begin by importing the necessary React hooks Useeffect, Usestate, and Useref. The Usestate hook initializes the state variable text, which will store the title fetched from the API. Next, we introduce the MountedRef using the Useref hook, initialized to true. This reference will help us track whether the component is still mounted during asynchronous operations like fetching data. Inside the Useeffect hook, we execute a fetch request to retrieve data from an API. When the data is received, we check the current value of MountedRef. If the component is still mounted, we proceed to update the text state with the fetch title. Lastly, we define a cleanup function within the Useeffect, which sets MountedRef current to false when the component unmounts. This simple yet effective pattern prevents memory leaks by ensuring that setText is only called when the component is still present in the DOM, allowing for safer asynchronous operations and optimizing performance throughout our application. Now let's take a look at how we can structure our React components to prevent memory leaks when dealing with asynchronous operations such as API calls. In our code, we define an app component that conditionally renders a title component based on the showTitle prop. This is a useful pattern for controlling the display of components dynamically. Within the title component, we utilize the Usestate hook to manage a piece of state called text, which will hold the title fetched from an external API. We then employ the Useeffect hook to perform the data fetching when the component mounts. The effect specifies an empty dependency array, meaning it runs only once after the initial render. However, one critical issue arises. If the user navigates away from the component while the fetch is still in progress, React will try to update text using setText, which can lead to a memory leak. To address this, integrating a pattern to check if the component is still mounted will help ensure that we avoid updating state after the component has unmounted, thereby preventing memory leaks and improving application stability. Now let's see how we can implement a simple click counter using refs. In this example, we use the Useref hook to create a mutable reference, countRef, initialized to 0. This reference will allow us to keep track of the number of times a button is clicked without invoking a re-render of the component. Next, we define the handleClick function, which is triggered every time the button is clicked. Within this function, we increment the value of countRef current by 1. This approach effectively maintains the count without affecting the performance of our application, as it bypasses React's state updating mechanism, which is responsible for re-renders. Finally, in the return statement, we render a button that, when clicked, calls the handleClick function. Additionally, we log the current count to the console, providing real-time feedback every time the button is pressed. This pattern is particularly advantageous in scenarios where state management could introduce unnecessary rendering overhead, making it a valuable optimization technique in performance-critical applications. Now let's see how we can implement a form handling component using refs to capture input values without triggering re-renders. In this example, we start by importing React and the Useref hook, which allows us to access and manage the reference to a DOM element. Inside the form component, we create a reference called InputRef using the Useref hook, which will be associated with our input field. As users fill out the form and click the Submit button, we prevent the default form submission behavior with ePreventDefault. This is crucial as it stops the page from refreshing. Instead of relying on state to hold the input value, we directly access the current value of the input through InputRefCurrentValue. This allows us to retrieve the value in a more performant manner without causing unnecessary re-renders that would typically occur with state updates. Finally, upon form submission, we display an alert showing the input value. This pattern not only simplifies our form handling logic, but also enhances performance, especially in scenarios with larger forms, by effectively managing data without contributing to rendering overhead. In summary, memory leaks happen when you unmount components while ongoing asynchronous operations are trying to update state. By using refs, you can keep track of whether a component is mounted and prevent unwanted updates. Furthermore, utilizing refs for mutable state values can help optimize performance by minimizing unnecessary renders. The power of refs in React should not be underestimated, as it enables developers to handle complex scenarios gracefully. By incorporating these techniques into your implementation, you can create efficient, leak-free React applications. Happy coding, and remember to minimize memory leaks and optimize performance with the use of refs in your. Now let's take a look at how we can create a custom hook called useCounter to manage a simple counter in our React application. In this hook, we utilize the Usestate hook to maintain a state variable called count, which initializes at a default value of 0 or any value provided by the user. Next, we define three functions: increment, decrement, and reset. The increment function updates the count by increasing it by 1, while the decrement function decreases the count by 1. The reset function sets the count back to the initial value specified when the hook is called. By returning an array that includes the count and these three functions, we can easily integrate this custom hook into any component that requires it. Now let's examine how we can implement this useCounter hook in a functional component named counterComponent. In this component, we import the useCounter hook and destructure its return value to extract the current count and the functions for modifying it. By linking buttons to these functions, users can click to increment, decrement, or reset the counter seamlessly while maintaining clean, reusable logic throughout the application. Next, we will modify our useCounter custom hook to accept a second parameter, allowing us to specify the step size for our increment and decrement actions. This enhancement increases the flexibility of our hook, enabling it to be reused in various scenarios with different step sizes. The function now takes two arguments: initial value, which sets the starting count, and step, which determines how much to increase or decrease the count with each action. Now let's see how we can implement this in our custom step counter component. We will initialize the useCounter hook with a starting value of 0 and a step size of 5. In this component, we return a structure that displays the current count and provides three buttons: one for incrementing the count, one for decrementing it, and a reset button to set the count back to the initial value. By clicking the respective buttons, the user can change the counter by 5 units, illustrating how the custom hook adapts to different use cases effortlessly. This modification emphasizes the reusability and adaptability of custom hooks in React, showcasing their role in simplifying component logic while enhancing functionality. Now let's implement the useForm custom hook that will help us manage complex form states efficiently. This hook starts by initializing its state with the provided initialValues object, allowing us to set our input fields dynamically. The handleChange function is central to updating the form state. It listens for changes in the input fields and updates the corresponding value in the state based on the input's name. This means that when a user types in an input field, the handleChange function captures the event, extracts the input's name and value, and updates the state without the need for multiple state variables. Next, we will see how we can utilize the useForm hook in our signup form component. Here, we initialize the form data with default values for username and email. By using the handleInputChange function returned by the hook, we ensure that any input changes are accurately reflected in the form data object. This separation of form handling logic from the UI component not only streamlines our code, but also enhances its maintainability, allowing us to focus on the rendering aspects while the hook manages the form's functionality. Now let's implement the following custom hook called Usefetch, which is designed to encapsulate the logic for fetching data from an API. This hook takes a URL as an argument and manages three pieces of state: data, loading, and error. We initialize data as null, set loading to true to indicate the fetching process has started, and initialize error as null to handle any potential errors during the fetch. Inside the hook, we utilize the Useeffect hook to perform the fetching operation whenever the URL changes or when the hook is first invoked. Within this effect, we define an asynchronous function called fetchData that employs the fetch API to retrieve data from the specified URL. If the fetch is successful, we pause the response as JSON and update our data state accordingly. If an error occurs, we catch it and set the error state. Finally, we ensure that loading is set to false once the fetch attempt concludes, regardless of success or failure. This hook returns an object containing the data, loading, and error states, providing a clean and organized way to manage data fetching logic in our components. Now let's see how we can use this useFetch hook in the data fetching component. In summary, custom hooks provide a way to encapsulate and reuse logic in React functional components, allowing developers to write cleaner and more maintainable code. So far, we have covered how to create custom hooks for managing states like counters and forms, as well as handling side effects like data fetching. By using custom hooks, we can keep our components light and focused on rendering, while placing complex logic in reusable, organized functions. As you continue to develop applications in React, don't hesitate to create and leverage your custom hooks. They can significantly reduce the redundancy of code across components and enhance the scalability of your application. So get excited to build better, reusable components, maintain cleaner code, and enjoy the power of React's hooks to elevate your. Creating a custom Debounced hook for optimal performance in React can greatly enhance the responsiveness of your applications. Today, we're diving into an important topic that revolves around the timing and handling of state changes in React components. We will explore the principles behind debouncing, how it works in applications, and how to implement a custom hook from scratch that ensures efficient state updates without overwhelming your user interface. So far, we learned about the use of custom hooks in React to encapsulate and reuse logic across components, enhancing code maintainability. We explored creating custom hooks like useCounter and useForm for managing state, as well as useFetch for handling data fetching. These hooks enable developers to keep components lightweight while organizing complex logic into reusable functions. Overall, custom hooks streamline development and improve application scalability. Now, we will explore how to create a Debounced hook that helps to manage state changes more effectively. To understand the necessity of a Debounced hook, let's first explore what debouncing is. Imagine typing in a search box where every keystroke initiates an API call to fetch data. If the user is a fast typist, this could generate multiple requests in a very short period, leading to unnecessary server load and possibly overwhelming the UI with updates. The essence of debouncing is to ensure that a function doesn't execute until a certain period has elapsed since the last time it was invoked. Here's a simple way to conceptualize it. Whenever a state change is dispatched, we wait for a period before finalizing that change. This gives clarity that the ongoing changes are indeed meant to be applied, thus creating a smoother user experience. Let's get into the implementation. Now let's take a look at the implementation of the Debounced hook. We begin by importing the essential hooks from React: Usestate, Useeffect, and Useref. The Debounced function takes two parameters: old state, which represents the initial value, and duration, indicating the wait time before the state updates. Next, we initialize the state with Usestate, setting it to old state. To manage the timeout across re-renders, we utilize Useref, which allows us to keep a reference to the timeout ID without causing additional renders. The core logic exists within a Useeffect hook, where we set up a timeout that delays updating the state based on the specified duration. If old state or duration changes before the timeout completes, the cleanup function ensures that the previous timeout is cleared, thus preventing outdated updates. This allows the state to only reflect the final input after the user stops typing, optimizing performance and enhancing user experience by avoiding unnecessary renders. Finally, we return the debounced state, which can be utilized in components to manage inputs more effectively. Now that we have our Debounced hook ready, let's implement it in a search feature component. We'll start by importing React along with the necessary hooks, Usestate for managing state, and Usememo for optimizing performance. The search component begins by initializing a state variable text to hold the value of the input field, while the debounced query invokes our custom Debounced hook, which delays the update of text for 300 milliseconds after the user stops typing. Next, we utilize the Usememo hook to filter an array called fruits based on the debounced query. This ensures that the filtering operation only recomputes when the debounced query changes, preventing unnecessary computations and enhancing performance. The results are derived by checking if each fruit in the list includes the current debounced query. Additionally, we define a handle change function to update the text state whenever the input changes, providing a controlled input experience for the user. Finally, the component returns a simple input field for the user to type their search query, along with a list of filtered results that updates reactively based on the debounced input, creating an efficient and user-friendly search experience. Now let's see how we can implement the filtering of results based on the user's debounced input. Here, we use the Usememo hook to optimize the performance of filtering our list of fruits. This hook efficiently recalculates the filtered results only when the debounced query changes, avoiding unnecessary computations and re-renders. The first step in our logic checks if the debounced query is empty. If it is, we return an empty array, ensuring that when the input is cleared, the UI reflects this by displaying no results. This prevents users from seeing outdated or irrelevant information after they clear their input. If there is a valid query, the fruits array is filtered to include only those items that contain the typed query, thanks to the filter method combined with the includes function. This approach ensures that as the user types, results are updated smoothly and responsively, with minimal lag, thus enhancing the overall user experience. By leveraging Usememo in this way, we ensure that only necessary updates occur, which is essential for optimized performance, especially in larger applications. As we wrap up, let's summarize the key lessons we've covered. We discussed the importance of debouncing in React applications, especially when it comes to optimizing performance during rapid state changes. By developing a custom hook with Debounced, we've enabled a more responsive interface that only reacts after a user has paused their input. The use of Useeffect for managing timeouts, alongside Useref for persisting timeout identification, allows us to elegantly control when state changes happen without cluttering the UI or overloading our backend with requests. Combining this with Usememo for derived state helps maintain efficient component re-renders. Building custom hooks like Debounced is not just a leap into more advanced React usage, but also a pathway to clean, maintainable, and high-performance applications. Thank you for joining me on this deep dive into custom debounced hooks. Make sure to implement this in your own applications. Feel free to experiment with the duration, and as always, utilizing custom hooks in React can significantly streamline event management, making your components more organized and your code cleaner. In this session, we'll explore how to create a custom hook for managing click events outside of a specified element. This is particularly useful in scenarios like dropdowns, modals, or tooltips, where you want to close the element if a user clicks outside of it. So far, we learned about the significance of debouncing in React applications to enhance performance during rapid state changes. We developed a custom hook called Debounced, which uses Usestate, Useeffect, and Useref to manage state updates more efficiently, allowing for a smoother user experience. Through a practical example, we implemented this hook in a search component to demonstrate its effect on reducing unnecessary renders and server requests. Overall, we highlighted the advantages of custom hooks for creating maintainable and responsive applications. Now we will dive into creating a custom hook named UseClickOutside for effective event management. Now let's take a look at our custom hook, UseClickOutside. This hook allows us to manage click events efficiently by detecting if a click occurs outside of a specified element. It takes two parameters, ref, which is a reference to the element we want to monitor, and handler, a function that gets called when a click is detected outside of that element. Next, we use the Useeffect hook to set up our event listeners for mouse down and touch start. This ensures that the hook works effectively on both mouse and touch devices. When the component mounts, we define a listener function that checks if the click target is outside of the element referenced by ref. If the click is outside, the handler is executed, allowing us to trigger specific behavior, such as closing a dropdown or modal. It's essential to clean up these event listeners when the component unmounts or the dependencies of the effect change, ensuring our application remains efficient and avoids memory leaks. By incorporating this hook in your components, you simplify click event management and maintain a clean, organized code base. Now let's implement the following code for our dropdown component, which leverages the useClickOutside hook we created. This component starts by using the Usestate hook to manage its open or closed state, initialized to false. We also utilize the Useref hook to create a reference to the dropdown element, allowing us to track clicks related to this specific component. Next, we define a toggle dropdown function, which toggles the dropdown's open state by flipping the isOpen variable. To handle clicks outside the dropdown, we create the handleClickOutside function, which sets isOpen to false, effectively closing the dropdown when triggered by an outside click. Now we invoke the useClickOutside hook, passing in the reference in our handleClickOutside function, ensuring that whenever a click occurs outside of the reference dropdown, the dropdown will close. Lastly, we structure our return statement to render the dropdown, with a button that toggles its visibility and conditional rendering for the dropdown's content when isOpen is true. This setup encapsulates the dropdown and its interactions elegantly, demonstrating the power of our custom hook in managing user click events effectively. Now let's see how we can implement a more dynamic user experience when handling clicks outside our dropdown. In the updated handleClickOutside function, we are introducing a closing animation logic that enhances the way our dropdown behaves when closing. Instead of instantly setting the dropdown state to closed, we can utilize a timeout to delay this change. This technique allows animation to play fully, providing users with visual feedback as the dropdown smoothly transitions out before it completely disappears from the UI. To achieve this, we modify the handleClickOutside function to wrap the state change within a set timeout. We can set this timeout duration to match the length of our closing animation, ensuring a seamless experience. In this example, we assume an animation duration of 300 milliseconds. This slight alteration not only enhances the UI, but also improves the perceived performance, as users enjoy a polished interaction rather than a sudden disappearance of the dropdown. Emphasizing such details in user experiences can significantly boost usability and engagement in your application. Now let's see how we can enhance our useClickOutside hook to handle multiple references. In this revised version, the hook accepts an array of refs, allowing us to manage outside clicks from multiple elements simultaneously. As we move into the Useeffect function, we define a listener that checks whether the click target exists within any of the elements represented by the refs array. This is accomplished using the sum method, which iterates through the refs to determine if any ref contains the clicked event target. If a match is found, the listener simply returns early, preventing the handler from executing. However, if the click occurs outside of all the specified refs, the handler function executes, allowing us to implement necessary actions, such as closing multiple dropdowns or modals. Next, we add our event listeners for both mousedown and touch start, ensuring that the hook responds appropriately across mouse and touch devices. It's crucial to clean up these listeners by removing them when the hook's dependencies change or when the component using it unmounts. This cleanup prevents memory leaks and ensures efficient event management throughout the application, ultimately providing a smoother user experience. In conclusion, custom hooks like useClickOutside are a powerful tool in a React developer's toolkit. They enable cleaner, reusable code while promoting better event management for user interactions. By encapsulating this functionality, not only does your component logic remain organized, but you also save time and effort by avoiding repetitive code across multiple components. We've seen how to structure our hook, utilize it within a component, and even extend its functionality to handle multiple refs. There's a lot of versatility embedded within custom hooks, and as you become more familiar with them, you'll find even more innovative ways to manage state and events effectively. So to wrap up what we've covered today, we've learned how to manage click events outside specified elements using a custom hook tailored to event management in React. We created the useClickOutside hook, integrated it into a drop-down component, and discussed ways to enhance user experience through animations and the potential for multiple element support. Embrace the power of custom hooks, design with intent, and keep your code clean and efficient. Understanding state management in React is crucial for building responsive and performant applications. In this segment, we will explore how to manage state effectively using custom hooks, specifically focusing on a custom hook we'll refer to as useCurrent. This hook allows developers to handle state updates in a way that's straightforward yet powerful. So far, we learned about creating a custom hook in React called useClickOutside, which effectively manages click events outside a specified element to enhance component usability. We demonstrated its implementation in a drop-down component, allowing it to close when the user clicks outside. Additionally, we explored ways to improve user experience by adding animations and extending the hook's functionality to handle multiple refs. Overall, custom hooks like useClickOutside promote cleaner code and efficient event management. Now, we will delve into managing state in React with our useCurrent hook. Now let's delve into the implementation details of the useCurrent hook. This custom hook begins by importing the useState function from React, which is fundamental for managing component state. Within the hook, we initialize the state with an initial state wrapped in an object, allowing us to store the actual state value. This structure facilitates efficient updates and retrieval. Next, we define a dispatch function responsible for updating the state. It's designed to only change the state if the new value differs from the current one, which helps in avoiding unnecessary re-renders. This is a crucial feature that enhances performance by preventing redundant updates when the state remains unchanged. We also implement a getState function that returns the latest state value stored in our object. This function ensures that we can easily access the current state, regardless of when it is called. This encapsulation of state management allows developers to utilize the useCurrent hook seamlessly, providing a streamlined approach to handle state in React components without falling into the common pitfalls associated with the standard useState. Next, we will implement a simple component called title that utilizes our useCurrent hook for managing a click count. In this component, we initialize the count state with the hook using useCurrent0, setting the initial count to 0. Importantly, getCount allows us to retrieve the current count value, while setCount serves to update this value. When the button is clicked, we trigger the onClick function, which sets a timeout of 3 seconds. After this delay, the function calls setCount getCount plus 1, incrementing the count by 1. What's particularly beneficial here is the use of getCount, which returns the latest count even after the timeout delay, ensuring we avoid the state lag issue inherent in conventional useState management. Finally, the current count is displayed on the button itself using the getCount function. This seamless integration of the useCurrent hook not only enhances the user experience by providing immediate feedback, but also exemplifies the efficiency of handling state updates without unnecessary re-renders. Now let's implement a component that manages both a counter and a toggle state using our useCurrent hook. This example showcases the versatility of the hook by allowing us to efficiently manage multiple pieces of state within a single component. In the counter and toggle component, we start by defining two state variables, getCount, which retrieves the current count, and setCount, which updates it, initialized to 0. Similarly, we define getToggle and setToggle to manage a Boolean toggle state starting at false. This setup enables us to track the count and the toggle state independently while still keeping the code clean and organized. Next, we create an onClick function that is triggered when the button is clicked. Inside this function, we use setTimeout to delay the execution of updating our states by 3 seconds. After this delay, we increment the count and flip the toggle state. This showcases how useCurrent provides access to the latest state values, ensuring our updates are based on the current states, resulting in a responsive user interface. Finally, the component returns a button, along with the current count and toggle status, demonstrating the seamless integration of both states in one interactive UI element. What's fantastic about crafting custom hooks like useCurrent is that it provides the advantage of encapsulation. You can integrate this functionality into your projects without worrying about state confusion across components. Additionally, since the hook centralizes the state logic, it promotes cleaner and more manageable code, aligning with React's philosophy of building reusable components. As we move forward, you might wonder about potential scenarios where useCurrent could be seamlessly integrated into larger applications, especially when handling asynchronous operations like API calls or managing complex forms. The beauty of hooks is their composability, meaning we can easily combine them with other hooks as needed. Next, we will implement a simple userform component that showcases how our custom useCurrent hook can effectively manage user input. In this component, we initialize state variables for the user's name by calling the useCurrent hook, which provides a getter function, getName, and a setter function, setName. The handleChange function is triggered whenever the user types in the input field. It updates the state by calling setName with the current value of the input field, ensuring that the state is updated smoothly. This linkage allows for real-time tracking of user input without causing unnecessary re-renders, thanks to the optimized nature of useCurrent. When the user submits the form, the handleSubmit function is called. This method prevents the default form submission behavior and displays an alert with the current value of the user's name by invoking the getName function. This approach not only enhances performance by minimizing re-renders, but also enriches the user experience, providing instant feedback as users type. Such a pattern effectively demonstrates the power of useCurrent in managing state in functional components. As we conclude our discussion on managing state with custom hooks like useCurrent, it's essential to highlight the importance of robust state management in creating scalable applications. Using custom hooks not only keeps our code clean and organized, but also encourages a pattern that can be easily replicated across different projects. Remember, the power of React lies in its component-based architecture, and when complemented with effective state management techniques, you can create dynamic and efficient user interfaces. Keeping things simple, yet flexible, allows you to harness the true power of React and build applications that can easily adapt to changing requirements or complex business logic. By mastering state management through custom hooks, you're on your way to becoming a proficient React developer. Keep experimenting and applying these concepts in your projects, and watch your proficiency in creating responsive user interfaces grow exponentially. With that, I hope you feel empowered to manage state effectively in your React applications using custom hooks like useCurrent. Happy coding, and until next time, keep building and innovating. Now let's dive into the topic of utilizing Proxy for state management in React. This is a fascinating area where we can enhance our React applications by improving how we manage state, making our code cleaner and more efficient. So far, we learned about the significance of state management in React applications and the introduction of a custom hook called useCurrent. This hook addresses the challenges of asynchronous state updates by storing state in an object, improving state retrieval and minimizing re-renders. We explored its integration in components for handling simple counters and toggle states, demonstrating its flexibility and efficiency. Additionally, we discussed how useCurrent enhances user experience in forms by providing real-time input management without state lag. Now, we will cover how using the proxy object can revolutionize state management, leading us to more reactive and organized components. Now let's implement the useProxyState custom hook, which serves as a main tool for managing state more effectively in our component. This hook begins by initializing a state variable using React's Usestate with the provided initial state. The core of the hook features a proxy, which wraps the state object, enabling us to intercept property assignments. Next, we define the set trap within the proxy that captures whenever we attempt to change a property value. In this trap, we update the target object with the new value. Critical to this setup, after modifying the state, we trigger a re-render by invoking the setState function, ensuring that the UI reflects the latest state. In the form component, we utilize the useProxyState hook to store form values like name and email. The handleChange function is configured to handle input changes dynamically by extracting the name and value from the event target. Instead of managing separate states for each input, we can now manipulate the form state directly as it is a proxy, making for a more seamless state update and rendering process. This way, managing multiple input fields becomes more intuitive and efficient. Now let's examine how we can handle nested state updates using a more advanced proxy implementation. We begin by defining a custom hook named useDeepProxyState, which accepts an initial state object. This hook manages the state using the useState React hook and creates a proxy for the state object. The createProxy function defines a set trap to intercept property assignments. When setting a property, it checks if the value being assigned is an object. If it is, it recursively creates another proxy for that object, enabling deep reactivity. Next, we implement the profile component, which utilizes this hook with an initial user profile object that includes name and email. The handleChange function captures input field changes. It splits the input field name, like username, into keys, allowing access to the nested property dynamically. It traverses the state using these keys, finally assigning the new value to the corresponding nested property. This setup lets us handle complex form states more intuitively, maintaining reactivity without the need for verbose state management. Overall, this approach simplifies managing deeply nested state structures in React applications. Now let's implement the useBatchProxyState hook, which enhances our state management by batching updates to minimize unnecessary re-renders. This custom hook starts by initializing two pieces of state, one for the main state and another for accumulating pending updates. The applyChanges function is defined to merge these pending updates into the main state after a specified delay, in this case, 100 milliseconds. This batching mechanism helps ensure that multiple rapid changes do not lead to multiple re-renders. Next, within the Useeffect hook, we monitor the pending updates. When there are updates to process, a timer is set to call applyChanges, and this timer is cleared if the hook is cleaned up before the timeout completes. This ensures that we don't run the update function unnecessarily. To facilitate the reactivity of the state, we create a proxy object with a set trap that intercepts property assignments. Instead of directly updating the state, it stores the new values in the pending updates. This approach allows us to modify user inputs in the UI, such as name and email fields, without triggering immediate re-renders, ultimately optimizing performance during user interactions. Now to wrap up, we've explored an exciting aspect of React state management through the lens of JavaScript proxy. We started with basic concepts, creating reactive state management for flat objects, and proceeded to handle nested structures effectively. Batching updates for performance showed us how modern applications must adapt to meet the demands of high interactivity. The integration of proxy into your React applications provides a powerful tool to manage state in a more elegant manner, ensuring our components stay responsive and easy to manage. As you continue your journey into React, keep this approach in mind, always considering how improved state management can lead to excellent user experiences. Whether you choose to adopt proxy for your projects depends on the complexities of your application's state. Evaluate your needs and select the approach that best meets them. To build a website with React, we need to do all the things that a web developer needs to do. That is, designing the site layout with HTML, making the site look beautiful with CSS, and adding business logic and interaction to engage the user with JavaScript. It might sound daunting, but React simplifies the entire process immensely. In this tutorial, we're going to dive deep into the essentials of building websites with React, covering everything from the foundations of the framework to specific coding practices. So far, we learned about the use of proxy in React for state management and various techniques that enhance our application performance. Now, we will cover how to utilize React for building a comprehensive web application. Now let's implement a basic functional component in React. The greeting component is designed to accept a prop called name and render a welcoming message that incorporates this prop. You'll notice that this component is defined as a JavaScript function, which is typical for functional components in React. The core of the component is the return statement that outputs a React element, specifically an h1 header displaying hello, followed by the value of the name prop. This dynamic rendering demonstrates how React allows you to easily pass data into components, facilitating code reusability. By exporting the greeting component, we enable its use throughout our application, ensuring a consistent user interface. This approach exemplifies the component-based architecture of React, which empowers developers to break down complex UIs into manageable, reusable parts, making it easier to maintain and scale applications. As you work on your projects, consider how you can leverage such components to construct your application efficiently while maintaining clear and organized code. Now let's see how we can implement a simple counter using React and the Usestate hook. In this code, we start by importing React and the Usestate hook from the React library. The counter component is defined as a functional component. Inside this component, we declare a state variable called count, which is initialized to 0 along with a method, setCount, that will be used to update this state. The JSX returned by the component displays the current count and includes a button. When this button is clicked, it triggers an event that calls the setCount method with count plus 1, effectively incrementing the count by 1. This showcase demonstrates how user interactions, such as clicking a button, can seamlessly update the component's state. The Usestate hook is crucial in this example, as it allows us to manage local component state easily without the need for a more complex state management solution. This concise implementation highlights the power of React to handle state in a straightforward manner and illustrates how user engagement can directly influence the component's behavior. Now that we have an understanding of component styling in React, let's take a look at how to create styled components using the Styled Components library. First, we import styled from styled components, which provides us with a way to define styles directly within our JavaScript file. Next, we declare a button component styled as a button. The styles are defined using a template literal, allowing us to use normal CSS syntax. Here, we set the background color to blue, the text color to white, and add some padding. This scoped styling ensures that the button's appearance doesn't conflict with other components in the application. Now let's implement a functional component called StyledButton that renders our button. This highlights how easy it is to create reusable styled elements in React without the need for external CSS files. Furthermore, we'll see how we can enhance our styling with dynamic values. By introducing a dynamic color variable, we can create a dynamic button that adapts its background color based on this variable, showcasing the seamless integration of JavaScript into our style definitions. This flexibility allows for a more interactive and customizable user experience. Next, we will take a look at how JSX simplifies writing React components by allowing us to blend HTML-like syntax with JavaScript. For instance, when we write a simple JSX statement like returning a header element, the code appears as h1 hello world/h1. This syntax is intuitive and helps in visualizing the structure of the UI at a glance. However, it's important to understand that browsers do not natively interpret JSX. Thus, when this code is processed, it gets transpiled into standard JavaScript using tools like Babel. The translation for our JSX example would yield a call to React create element, producing a similar output but in JavaScript syntax. React create element h1 null hello world. This transformation illustrates the power of JSX in enhancing development efficiency, allowing developers to seamlessly integrate UI design and logic. By using JSX, we maintain a level of readability and coherence within our components, making it clear how the layout and behavior are intertwined, which is fundamental in React's component-driven architecture. Now let's see how we can implement an authentication context using React's create context and use reducer. We begin by creating a new context specifically for managing authentication states. The authReducer function handles state transitions based on different action types, such as login and logout. When a user logs in, the state is updated to reflect that the user is authenticated, while logging out sets the authentication state back to false. Next, we define the authProvider component, which will encapsulate our application and provide the authentication context to its children. Inside this provider, we use the useReducer hook, initializing our state to indicate that the user is not authenticated at the start. This enables our application to react to authentication changes seamlessly. The authContext provider wraps around any children components, sharing both the authentication state and the function to dispatch actions. This setup fosters centralized state management, allowing components to access the authentication state without having to pass props down through numerous layers. This streamlined approach makes managing global states much more efficient in complex applications. Now let's see how we can implement accessible buttons in our React application. The code provided creates an accessible button component that enhances the usability of buttons for all users, particularly those utilizing screen readers. This component accepts two props, onClick, which is a function that gets executed when the button is clicked, and children, which represents the content displayed inside the button. Within the component's return statement, we create a button element that is equipped with an onClick event handler linked to the onClick prop. A significant feature here is the inclusion of the Reusable attribute, which takes the value of the children prop. This attribute is crucial for accessibility, as it allows screen readers to convey the purpose of the button to users who may not see the visual content. By following this practice, not only do we make our application more inclusive, but we also align with web standards that emphasize responsive and accessible design. Integrating such accessible features enhances the user experience and ensures that our application caters to a wider audience. In conclusion, building websites with React is an enriching experience that combines the power of JavaScript, the flexibility of styling, and the capability of handling states with ease. You now have the essentials to create a React application, manipulate asserts of user interaction, and ensure your application is styled and responsive. As you continue your journey with React, remember to experiment, build, and most importantly, enjoy the process of creating remarkable web applications.